Oh, I see. Okay. Can you put your heads on and make sure you can hear him all right?
1, 2, 3, testing. Can you hear me? 1, 2, 3.
Okay, you're all good.
Yeah, I think it's on the speaker.
Austria. He moved to Vancouver, Canada in 1990 and has since been involved in professional communication and digital wireless network systems. In 2005, he started work at the Biomedical Engineering Department in Children and Women's Hospital in Vancouver. Please welcome Alex Schwartz.
Okay. All right. Here we go. Yeah, to have the opportunity to talk about the solar eclipse and about the beautiful solar events we had right after the solar eclipse was a great opportunity. And maybe we can bring it all a little bit closer to all of you and make you understand what the fascination of the sun is with regards to shortwave radio. And this is a picture of the solar eclipse taken by Stan KM4HQE. And this happened last year, August 21st. And it was, who did see the solar eclipse? Oh, yeah, it's quite a bit. Did actually somebody go to the totality, to the area of the totality? And yeah, and it's, they say that totality is quite an experience. Oh yeah, and yeah. And unfortunately, I didn't make it to totality, but I was thinking about it. But we were doing something else. We were measuring the propagation changes or trying to measure the propagation changes during the solar eclipse. And this brings us to the first slide. So there you go. So now we're going to set up. We have to give a little bit of an intro for the people that do not know what we're trying to do is what we developed is a noise monitoring tool that would monitor the RF noise and the RF propagation during the solar eclipse. And in order to do this, we had a scanning shortwave radio and monitored the shortwave radio bands. And in order to monitor shortwave radio bands, we can determine the propagation. So this is set up the day that we had. It was beautiful, clear sky in Vancouver, British Columbia, and it was the perfect day to watch a solar eclipse. We had, for the solar flux and the solar activity was problematic at that time because the solar flux used to be down at 80, and within a couple of days just before the solar eclipse, the solar flux went up to 90, and it was still rising. And there was at one point where right after the solar eclipse, where the solar flux actually went up to 138, but it never showed. You never see that in the graphs because the graphs are long time delayed, so you don't see anything happening. But there was reports that it was the strongest solar flux reported, even stronger than during the high times of the solar cycle. So that's what brings us to the solar weather. So also about the D layer. So what happens is with the D layer is one of the communication layers that we use to communicate with after horizon stations. And the D layer has an effect that when it's activated, it attenuates the radio signals. So the stronger the D layer is, the less radio waves you can be able to get from one location over the hill to another location being reflected. What happens is these radio waves have to go through the D layer, and they get attenuated. And on the way down, when they get reflected from the F or G layer, it goes down and it gets attenuated again. So if that layer is active, it's very problematic to get any shortwave radio propagation. And the more active the D layer is, the lower the frequency that you can work a station throughout the world. And the Eclipse totality was 85% in Vancouver, but nevertheless, it was still a good location to monitor the propagation changes during the solar eclipse. Okay, so, okay, all right. So this brings us, and this is just, that's this slide, I just added that slide recently. And the reason why this is important is because the image spacecraft, everybody knows the image spacecraft because it has been in the news in the last little while. There was a Canadian ham, not too far from where I live, who found the radio signal of image, and it turned into a worldwide thing. So I looked at the image spacecraft and I thought, oh, this is the fantastic tool. I'm pretty sure they looked at solar eclipses with this infrared, not ultraviolet camera, and sure they did. And thanks to Berkeley, who was archive all this data, we were able to get this this clip here. I was working before. Come on.
That's our motto here.
There it goes. Okay, there it goes. Okay, so this is this is actually what we actually wanted to measure, but we wanted to do it on a ground level, and we wanted to confirm it at the shortwave bands. And what you can see is the ultraviolet imager detecting the electronic decay of the ionosphere, and as the sun moves in here, you can see how the ionosphere is affected and changed by the lack of radiation that is blocked from the moon, that the moon blocks and is missing from the sun. And so we tried to see if we could measure this in the shortwave bands. And I can if you guys want to use this for your own, it's part of Berkeley server, and I can give you the link for this beautiful image. Okay, let's go here.
Red button top left.
Okay. I should be using a Mac.
Yes.
There it goes.
There's a play button in the upper right.
Okay, play slideshow. Okay. All right, there we go. So what we seen was the image was recorded by the far ultraviolet camera on board of the image spacecraft, and the way it works, it's kind of like similar to the way it works in a neon lamp. So when the excited electrons recover their electrons and they jump from one band to another, it releases ultraviolet radiation, and that ultraviolet radiation is covered by the far ultraviolet camera on that spacecraft, and that's why we can see the changes in the ionosphere using this instrument. And there's also I don't have that here, but if somebody's interested, there's an image or little movie put together called the Bastille Event, and that happened in I think it was in 2001. They had really strong the solar flares, and it activated the nose polar what you call it? The Aurora Borealis, yeah. And they recorded it with this, and it's amazing. It goes on for days. And so I think I put the link at the back of my presentation, so you could go there and download that too. Okay, here we go. So this is what ham radio operators did in 1999, and this was recorded by Guy Rawls. And interesting enough, Guy Rawls is one of the co-writers of our software. So it was I didn't know that. We were starting the RF seismograph project to monitor exactly these kinds of events, and I didn't know that he was part of that already. So when we decided to develop the software to monitor the solar eclipse, he said, "Oh wow, this is great! So you should see what we've done." So he gave me all these images, and he was so this was actually recorded in Belgium. There was a total solar eclipse in 1999, and it shows it shows how the noise level changes, and this is on 40 meters. So this is before the eclipse, this is during the eclipse, and this is after the eclipse. So this was our benchmark of what we wanted to accomplish. And go to the next slide. And this brings us to because it's 10 years later or 15 years later, and we have much better technology available. We decided on like how far do we want to go with this new measurement? How far can we take it to improve on the measurements? So the first thing that we wanted to do is we want to be able to see multiple bands at the same time. So the way we did it, we instructed our software to scan the radio receiver. So what happens is it scans 6 bands that you want to monitor. In this case, we monitored 80 meters, we monitored 40 meters, we monitored 30 meters, 20 meters, 15 meters, and 10 meters because I had the antenna for it. And this is the multiple station measurement topology. So what we're trying to do is have the capability of the RF seismograph over the continent, distributed over the continent, so that we can have similar the way we have weather stations all over the place. We can measure the propagation in different locations, and the way you make this work is you have to make that each station is independent, and it's not relying on any of the operators. So they just log on to the internet, and the image is automatically uploaded. And at the end of the experiment, the data was uploaded. So this is what we have: real-time graphs, and then the data is uploaded at the end of the measurement. And we're basically capable of doing that all around the world. So our RF seismograph software is already capable of monitoring propagation all over the world. All what we need is people willing and dedicated to do that, because when you monitor your RF bands, you can't use your radio, so it's a bit counterproductive. Like all the propagation that's out there, but you can't operate your radio because you want to monitor the propagation for others. So in this way we came up. It would be a great opportunity to have these monitoring stations, like in club situations where clubs have access to a repeater site, and you could set that up quite easily. Okay, so with the measuring location, since we don't have $1 million budget, we were a little bit limited with the people that were willing to put their radios to work during the solar eclipse. And so we had the MSR test station in Lynn Valley. This is the test station that runs right now, and it runs 24/7. So it monitors the radio band at all the time on the 6 bands that I mentioned earlier. Then I set up the mobile test station at the Cypress Cross Country Ski Area. That is a ski area that's about 40 kilometers northwest from the Lynn Valley head station, and it's up on the mountain, so the location is almost at 6,000 feet. So we wanted to see if there's any changes when you go up in elevation. And we also we have to thank Joe Jankas for letting us use his station. And he was in Newport, Oregon, which was in the Totality. So this gave us a very good understanding of what the changes would be. Like off Totality, there was only 85% in Vancouver, and in Totality where Joe Jankas is. And since the thing ran automatically, once you set it up, you just let it go. Okay, so here we go back to so this is the main monitoring station. And we got, this is the antenna. It's a 18 JR, and it's 36 feet tall. It's a huge antenna, and it works on all the bands that we monitored. My test radio is a FD950. You connect it to the software via CAT control. The MDSR and RF seismograph software that we developed was running at that. And we also used the BiLiF unit. So this is the little electronic box that takes the IF out of the radio and converts it down to a frequency that you can process with your sound card. So when you get the super dynamic range of your sound card, monitoring this space weather. And the Windows 8.1 and running seismograph software. So this is, if you're looking for a vertical antenna, this is a fantastic antenna, and it's actually quite reasonably priced. So this is the setup at the mountain. So I drove up there at 5 o'clock in the morning just to make sure everything works. And so this is the first picture that I took. So, and in this case, the antenna is an MFJ 1979 with a loading coil to make it work on 40 meters, because 40 meters is the most important band if you want to measure solar eclipses. And we got, in this case, the radio was a FD8117, and it was connected to the CAT control software, via CAT control, and the RF seismograph software was running. And we used our portable BiLiF unit. I'll show you pictures of that later, to interface between a computer and transceiver. So again, we take the IF out of the receiver and turn it into a frequency that the audio card can process and plug it into the computer. And then a laptop 10, Windows 10 laptop, running the MDSR software and the RF seismograph. Okay, this is Joe Jankas, and this is his location in Portland, in Oregon, and right on the coast, really close to Newport, and he had Totality, and he was also running an FD950 radio, and he was connected to CAT control via the RF seismograph software. So very similar to the same setup that I have at home. And he was using Windows 10 and the same setup, but he was located in, and he was actually able to stream the data images live onto our website using our software. Okay. So now that we talked about how our measurement worked, Now we're going to turn into make it into a bit more interesting by be a little bit more real. And this is image here, this video here. If that should work. Yeah, there it goes. Okay. So this is by Sky Calculus, an image by Sky Calculus, and it's their balloon flying during the solar eclipse. And as you can see, oh, I have started. And they do a really good job in exploring space science. Oh, I don't think we got any audio. Oh, there. Do we got any audio? Okay, so anyway. So this is the Sky Calculus people, and they launched their weather balloon. And they're photographing the solar eclipse from the space. And that's quite amazing. And you can see how defined the shadow is. And there's another problem here, right? Because the shadow is so small, the effect of the overall radiation that the Earth would get with the solar eclipse is still large. So to measure the propagation change in the area where you have only 170 miles wide darkness is very tricky. So, and especially in an area when you have high solar activity that blocks out all the bands that you wanna measure on. Okay, there it goes. So at the end of the experiment, the balloon explodes. Yeah. But yeah, it's there.
Otherwise, you don't get your camera.
Okay. All right. So now we're gonna go. Now we're gonna talk about the shadow size. So in order to put this in perspective of how much radiation drop there actually is during a solar eclipse, actually we calculated it. So what I did is I calculated the surface of the Earth, which is about 510 times 10 to the power of 6 square kilometers, and divided that by half because only half of the Earth gets hit by sunlight, and then we get the area which radiation covers, and then we calculate the surface of the lunar shadow, which is 50 kilometers radius, square kilometers. So we get almost about 8,000 square kilometers worth of area that gets darkened out by the sun. So now we make the ratio of the total surface that receives sun and the lunar shadow that blocks out. So we get a ratio of 1 to 32,000, and this is very small indeed. So if the solar activity is not is high and it blocks out the radiation, it's going to be really hard to measure see any changes, and that's exactly what happened during our solar eclipse last year. Okay, so this is when we looked at the sun, and this is a picture was taken actually 2 weeks later. So since the sun rotates, all these sunspots would have been on this side. But you can see how huge these sunspots are, and the solar radiation was intense. And it started in about beginning of August 2017, where the solar flux was actually rising, and the sunspots were active, and there were also big sunspots here. So during the solar eclipse, we actually had a M-class solar flare, and we actually recorded that through the DRO observatory in Penticton. So this is just to iterate the solar flux. So we got so this is the top of the solar cycle, and it drops down quite rapidly, and it's a long-running average. So it takes a lot of changes in order to get this up. So if the changes are only if there's high solar activity for a month, you will see it go up only like this. The high solar activity will not be shown because it gets filtered out. So in order to make the way this graph is developed, to make this kind of change where you see the little peak right there, it takes a huge energy to make it change like that. And here we go to the next one. Okay. Here you can see that that is that's an M-class flare that happened 3 days before. Oh, that happened 3 days before the solar eclipse, and you can see this is called the D-layer absorption tool, and it's provided by Noaa. And what they do is they take the radiation that comes from the sun, and also the season that we're in, like in summer, we get way more affected by solar storms than we get in the winter because the sun is on the other side of the planet, more on the it's down. It's like in the south, so we get a better, not as good of an angle of the solar eclipse. But anyway, this one happened right over the Pacific here, and that was in August. So it was summertime in the northern hemisphere. So we get really blasted with that one, and that one wasn't even the worst one. This was just one that really shows, the absorption. And here on the right here, you can see the absorption by frequency. So usually what happens is, when we get hit by a strong solar flare, the X-ray radiation causes the D layer to rise, and it starts to attenuate the lower bands first. So the first band you lose is 160, 80 meters, 40 meters, and so up. So. And this is actually, and it also depends on what time the flare hits. So in this case, it hit North America. Okay, so this is the measurement from the DRO in Penticton. That's their new solar flux monitor system. And they monitor different frequencies. And you can see the solar eclipse starts here. And this is, this frequency, the frequency that they're monitoring is I think it's 2.5 gigahertz. So you can definitely see the change of the radiation of the sun dropping. And then there at the end, just when the solar eclipse is just about done, you get that M-class flare spiking the measurement, and then the measurement goes down. And this is you can see the change because the solar flux is a sum of all the radiation that comes from the sun. As the moon covers it, the radiation goes down, of course. Okay. Okay, so and here we have the that's what the graphs that the RF seismograph puts out, and this is a comparison of the WA7HMB, so it's show Jankas station, and the MDSR test station in Vancouver, which are base stations. So we keep that like to make it most comparable. And you can see here at Joe's Jankas station that his antenna is working perfectly. Like he gets 9-time propagation. Just to give you a little bit of an understanding of what the colors mean, blue is 15 meters, green is 40 meters, red is 80 meters, and yellow is 10 meters, and purple is 20 meters. And you can see the beginning of the solar eclipse is here, and it's over. It's over here, and over there. And you can see that the activities are quite there, and it's strong band activity right here on 15 meters, and it drops right off, and it doesn't seem to affect anything. Like it don't see any changes. Like what we would have liked to see is the changes, especially the MUF frequencies moving from the higher level to a lower level. So like you would expect, if you get less solar radiation, the bands would would turn would change over to nighttime conditions. But because the change of the solar eclipse is so local, we couldn't measure that, and especially with a D-layer excited Earth. Measuring shortwave radio bands like 80 meters, the changes. We couldn't see that, so it was just not a given. But nevertheless, the activity of the sun just kept on going. So here's the measurement again, and this time it's my station in Lynn Valley. And again, like we can see nighttime propagation on 80 meters. And it comes down to here. And there's no change. Like, see, the flat line means that there's no noise change. So when the noise doesn't change in level, that means there's no propagation. So the propagation is totally blocked out. But it's not because it wouldn't be possible to see it. It's because the solar radiation and the activation of the D layer was making it impossible to measure. And here you go, 80 meters, 20 meters, 40 meters here, and there's nothing nothing different about the measurement than the day before. So it was in a way it was a bit frustrated. So what we had to do is we had to take a step back and we had to look at the big picture, and that's exactly what we've done. So if a measurement doesn't happen, we got to figure out why weren't we able to replicate the measurement of Guy Rowell in 1999 here in North Vancouver. Here in North America. And so this is where we come to the solar unrest. And you all might recall it even made the news, the regular news. There was a solar flare on September 6th. There was a solar flare that was so strong. That was the strongest solar flare probably ever measured, or at least in the last 30 years. And with some Noaa was actually the Noaa output was at one time probably stronger than X-ray flare. So X-ray flare is the strongest defined flare that we can get from the sun. But this flare was actually stronger than X-ray flare by just a little bit. And so it was huge. So the X-ray flare hit at 800 Zulu. And this was actually lucky for us because when it hits at 1200 Zulu, the peak of the radiation goes on in the Atlantic. So, like we don't get affected by it that much. But nevertheless, the solar proton flux and increased on an already unknown state. Like we had a class 2 storm, almost class 3 storm, continuing for about 6 hours. Like each measurement is 6 hours, and it was going on forever. And this is the X-ray flare that hit. And usually what happens is when there's a solar flare on the sun, the first time we know about it is when the light hits the Earth and our measurement equipment. And so this is what happens here. And then here. And then down here, this is the geomagnetic activity, which is affected mainly by particles. So this is delayed. So it takes a day or two, depending on how fast these particles move, to hit Earth. And sure enough, we got a delayed reaction about almost 2 days later. And the solar particles hit Earth so hard that it created a G5 storm, which is unheard of, and it surely blanketed out everything that we could work on shortwave radio. Okay, and here is it again. This is actually the picture of the solar flare that happened there, and this is the ghost measurement that actually is recorded by ghost 15, and here this is the second peak. Like it's a 2-peaking flare. The second peak was stronger, and this line here defines the top of the X-ray flares. So you can see how powerful this flare was. To put it in perspective, this is a logarithmic scale. So each line represents 10 times as strong as the line before. So it's similar to the way we measure earthquakes. And this was heading off the continent, so it wasn't really affecting. We didn't really see it too much on the RF seismograph because it was on the other side of the world. Okay, here we go. Wrong. There we go. There we go. So this is the measure. This is the plot from the RF seismograph during the X-ray flare, and you can see here. All of a sudden, as soon as the X-ray flare hits here at lunch time, the 15-meter bands all rather sudden go crazy. And I've never seen it jump like that, and like be so intermittent. And you can see it jumps up for about 5 minutes, 10 minutes, and then another 20 minutes, and then again we get 2 jumps of 20 minutes, showing the propagation, and then over here this is just the regular measurement, and then the solar storm hits, and it activates the delayer, and it basically mutes all the measurements, so you can't see really what's going on because you're behind. It's kind of like being behind fog. Okay, so this is the setup that we use to monitor space weather via our RF seismograph software, and it's a very simple setup. And basically, what you use a big shortwave antenna, preferred omnidirectional antenna, because you want to be able to see all the surroundings. And You put that in your shortwave radio, and then we have the LIF 2014 or 2016. Take the IF out of a radio via the option filter port, connect it to the 12 kilohertz IF to the sound card, and that will get you the audio into the computer, and you can measure the noise level. And you also have the cut control because we want to be able to switch bands and to make sure the radio is in the right mode to work communicate with our software. And this whole software is free for download, and it can be downloaded from our website, which is here. And we have capabilities. Our software is capable of connecting to 10 or 15 different transceivers, shortwave transceivers, that can also be found on the internet, and there's also on our website, and there's also instructions of how to integrate your radio with our software so that you can monitor space weather. So this is our through-hole version. So this is the LIF 2015 board. It's really easy to build if you want to build it. But we also have an SMD version, which is the next slide. And we also in order to use our MDSR software, which is the modulation demodulation software radio for TX, you have to build this unit. And this unit plugs on top of this unit, so and it makes a BiLif. That's what the BiLif unit comes together, and it allows you to use MDSR software and a sound card to generate shortwave SSB signals and broadcast them over your radio. Okay, so this is our new version. We actually specifically developed this for the RF seismograph and the solar eclipse testing and monitoring. And we have lots of people that bought that unit. We just couldn't motivate people to set it up to monitor the solar eclipse while it was happening. And and this is actually small enough. So if you have a Yaesu radio, an FT817, or with the filter slot that they provide, that actually fit right into that filter slot, so you don't have to do any soldering and you have to change this. All you have to do is provide 12 volts up here, and you connect your sound card to there, and you're in business. Okay, so there's some references, and this 11 years of sporadic E is a really good read, and it's about a ham radio operator down in southern states, and he did for 11 years. He monitored the bands for sporadic E, and it's amazing the amount of data that he collected by hand and every day, dedicated, making this measurement work. And I think the data was collected in the 1990s, and it was all done without computers. And the guy was really dedicated to make this report. Then here we got the NASA solar eclipse experiment in 1999. That was part of Gauss-Raoult's measurement. And here we got the Gauss-Raoult experiment together with ON500. So those are both Belgian hams. And then this is the DRO website. We have the Noaa communication dashboard, and if you're doing shortwave radio, this is the dashboard you want to be monitoring. If something happens at the sun, this is the first time you know about. And then spaceweather.com is a very good website. It's aimed mainly for people that like to watch auroras, but since auroras and solar activity and propagation are very similar, it's also a good site to watch, to see, to understand what happens behind what happens at the sun in order to change the propagation. And then our software can be downloaded here from our webpage. And that was it. Any questions?
For questions, can we ask that you wait for the microphone, please?
Okay. Sure.
Thanks. Hi, Alex. I'm Greg, VA7BC. I live about 10 Ks from your monitoring site, and I use the RF seismograph daily.
Okay.
My question is, I noticed there's sometimes a lack of correlation of propagation at my station compared to what the RF seismograph is showing. So I'm wondering if there's been any research done into relatively small geographic changes in shortwave propagation.
Yeah, there's actually quite a bit of research done, and we found out in 2016, I think, when we just started running the RF seismograph. We found out we had it running up on Cypress Mountain, or at the site where the where our ham radio club has their field day set up, and we had it running there. And because it's located on a very steep slope, so what happens is when the wind comes in, the wind gets blocked and gets pushed up the mountain, and this motion creates rising air. And if there's water droplets in the air, and there's most likely water droplets in the air because we're on the west coast, these water droplets can create RF noise, and you can actually blanket out your signal. So we found out that the location we're at, even though it's a perfect location, if you want to do 6 meters or 10 meters, the lower frequencies are a little bit handicapped, because if the fog comes in and the wind blows, the noise of the clouds is deafening, and it really blocks out propagation. So in order to really measure space weather, you would need a similar network that we have measuring temperature.
Test. 1, 2. Working. Perfect, thank you. Now, you want to switch it off again? Because otherwise.
Dennis? Dennis? This sounds terrible. Except that this is what it sounds like. There's like mice in the ceiling, is what it sounds like. All right, are we good here? This works. All right, let's go ahead and get started again. We don't want to keep you all day. I mean, you're welcome, but... All right. All right, who's transmitting? 528 megahertz.
Trying to go sideband on you.
All right, getting ready to go here. Our next speaker is Guus van Doren. He's the owner of Doren Electronic Solutions and started the company in 1998. The primary focus has been the design and production of electronic circuits, interfaces, and controllers running real-time software. Since 2013, Guus has been developing and producing digital voice-related hardware for D-Star, DMR, and System Fusion, known under the family name of DV Mega. His latest product is a radio that has no radio in it, so that's an interesting idea.
Interesting.
And he's going to talk about it today. So please welcome Guus van Doren.
Thank you. So I can skip a part of my introduction. Thank you, Scott. I started in 1990 as a industrial engineer at Philips at the development of compact disc. I moved in 1998 to Schlumberger, where I was a project leader of payment systems, of payment terminals on gas stations. From the year 2000 until now, I'm the owner of Doren Electronic Solutions, and 4 years ago, 5 years maybe, I started with the digital voice. So that's where we're going to speak about today. We had the introduction. I tell you a bit about the goal of the DV Mega project, the DV Mega evolution, where I started with, where I went through and where I'm now, the development challenges, and I explain a DV protocol example. In this case it is DMR, and I show you where all the bits and bytes and what they are doing from the moment you press your microphone until you release the microphone. And the new things I have under development. So the goal of the DV Mega project, it was for myself. I had no intention to do it commercial or whatsoever. I want to learn about digital voice, the modus and the protocols. Stimulate homebrew of HAM-related products, and later on provide affordable DV-related kits. At that moment there was a dongle, there was a... By the way, let me ask first, how many people are using digital voice? D-Star, DMR, Fusion? That's a lot, it's almost 50% I guess. So that I know what kind of terminology I can use when I talk about a reflector or a network, then that should be clear. Okay, I thought about what I'm going to make. First instance was to to learn about it, and I show you I used a existing product from where I started, and later I made a low power DV radio hotspot. Sorry, first a DV node adapter for a high power hotspot, so a modem with a 9K6 capable radio. Later on merged that, used a small radio, I show you later, a radio chip actually. I thought then at the time, yeah, why not using a direct digital voice device, a DV IP radio, because almost all repeaters are connected to a network, speaking together. Many people are using hotspots in their house, for in and around their house. So it's sorry. A new sort of radio, I think, will have a future in digital voice. And it must be all Arduino based. Why? Because an Arduino is very easy to program. You don't need special programmers. You have lots of I/O available. Oh, I think I need this one. Lots of I/O available, and again to stimulate homebrew projects. And an Arduino is low cost, is quite relative cheap, and has lots of standard libraries. So I thought that would be a good base to start from. The evolution of the DV Mega started in May 2013 with a hand-built solution of the GMSK modem from that time. And I think when people are using D-Star, they know the GMSK modem from Fred van Kempen, from Satoshi. No? Yeah, I think so. So what I did, I built that one in two pieces. The modem piece and the CPU piece, because it is still PIC-based. PIC processor. Sorry. But I want to go to the direction of Arduino. So I reused the modem part and wrote my own code in the Arduino. So the code in the PIC processor was not mine, but I built it like that to see what kind of signals you have to deal with, the control signals for the modem chip. When I understood what's going on in this case the GMSK modem, I wrote the software in the Arduino. It's an Arduino Mega with an 256K controller. And I built also one with the same modem hardware with the small controller, the 328. This controller will actually be the base, the minimum requirements for further products. I used the Mega to skip the radio, so the three modems here are all DV noded, so that means you need your modem, you need host software, and you need a 9K6, actually 4K8 capable radio as transmitter receiver. Because all hotspots, not all, but the majority of the hotspots are used in and around house, distance 10, 12 meters, not more. So I thought we can use a radio, and I used a AD7021 radio. It's a small SDR radio chip, which can do 2 FSK, 4 FSK, GMSK, and even FM. Based on the same Arduino Mega, reused the core of the source code and only modified the signals that are going to the GMSK modem, and in this case to the radio. You see the signals later on. November 2013, in January 2014, I skipped the Mega 2560 and went to a Arduino Uno that's provided with the Atmega 328 chip. And this is quite a funny board because these are all based on a USB connection to the host board controller, whether it is a PC. You had at the time the G4KLX host software. Later on there are more, but all the boards were based on a USB connection to the host. This was a time the Raspberry Pi came at the ham scene, and I thought I combine one radio with the Atmega chip, which is actually on the Arduino Uno. And it's quite funny because I didn't have the intention to make such a board, but I had to test a new PCB supplier, and I thought, what kind of circuit do I put on the board? So I really copy and pasted the UHF part of this radio, dropped it on that board, and a microcontroller, and it was really quick and dirty. You can see because I didn't use an SMD crystal, and I need a level shifter, a level converter, sorry, for the 5 volt and 3.3 signals between the radio and the controller. But at the beginning, it was just to test a PCB supplier. I went with 10 boards to the Rosmalen Ham Rally in the Netherlands, and they were sold out in 1.5 hours. So I thought, what am I doing wrong? And they are now sold in thousands worldwide. They are used in 65 countries via 18 resellers, where Gigaparts is one from. March 2014, only D-Star at that moment. This one, actually I released the schematics, everything, to stimulate homebrew modems making digital voice modules. And I don't want to say the funny thing, but the thing I saw was that I know of, only 2 people built it like this by hand. Everybody was asking for a module, a complete board. When do you have a complete board? Okay, I will make one in July 2014 with a complete GMSK modem, again based on a 9K6 capable radio, D-Star. Then I start playing with the MB 2020 that time, and the 3000 was, I think, maybe not new, but new for us. Much easier to control. And I made an Arduino Mega based MB3000 board that differs a bit from the existing dongles because I have audio on board. So you can use this MB as in codec mode and MB mode. Codec mode means you connect it to a PC, you send a PCM packet to, and you get an MB packet back. In the codec mode, you apply analog audio and you get your, in this case, D-Star packages back ready to send to pack in a protocol sent to the network. This one was made on request from some people in the United States because they're living in an area where you have anti-missile radars on UHF. I don't know exactly where it was anymore, but they need to go to VHF, an hotspot on VHF. That moment only a high-power hotspot was able to make on VHF because you decide yourself what kind of radio you connect to. And this one is a dual band, a UHF section and a VHF section. It's or, so it's not a full duplex hotspot. January 2015, I made the first standalone application for the direct voice device. So you connect a mic, a speaker and power supply. You go via USB to the G4KLX application at the time, and you have your own D-Star IP radio module. So you are able to talk to reflectors and other repeaters, hotspots, without a real ICOM radio at the time. October 25, I implemented DMR. In 2014, there was absolutely no sign of that we were going to DMR. Some people were playing with that. But in 2015, it took really a change to DMR. And in September 2016, System Fusion. Say, hey, that's quite a long time without anything new. We were very, very busy to supply all the people with boards. And I had already all the modules, the DV node, the modem, the low power radio, and the other two modes. So actually more new things were not at that moment. So the development challenges, taken into account that I started with D-Star and that DMR and Fusion are added later, is that it was quite a small processor. 8-bit architecture, 16 megahertz speed, 32 kilobyte flash, 2K RAM, and this was really a heavy one. Hard to deal with to get the protocol and all the mathematics in. E-square PROM and 2 external interrupts. The task list of the CPU is taken into account. The small capacity, low capacity, is quite a lot. It's a radio server, serial port handler. The radio server is a module which communicates with the ADF chip, so it controls the chip and it takes care for the radio data. Serial port handler, communication to the host software. State machine, am I RXing, TXing, am I waiting? Do I wait for a sync word or whatsoever? And the algorithms used for D-Star DMR Fusion is Viterbi, Golay, Hamming, BPTC, interleaving, CRC computation, parity bits, all kinds of things, but we see a lot of them later on in the walk through the DMR conversation. The radio server. The radio is based on the ADF 7021 radio chip. Again, it's a small SDR radio doing some different modus, 4 FSK, 2, 3 FSK, GMSK, and it's a very, very funny chip. You can do almost everything with that, from speeds of 1.2 about of bits per second to 100 kilobits a second. Build up very simple. The RF states. Here you have the TCXO. It has to be very, very stable, precise, because everything, the bandwidth, the data rate, the frequency, everything is derived from that TXCO. Loop filter and a VCO, external VCO coil when you go, I believe, under the 160 megahertz or whatsoever. then the internal coil cannot lock the VCO anymore, so you need an external one. This port, actually both ports are communicating with Atmega chip. This is the port where you say you have to be a 2FSK receiver transmitter now. You set the bandwidth, everything with this port. And this port is the data port. So it takes care for a clock and a data signal extracted from the radio data. So you don't have to do anything. You'll be served with a clock and a data pulse, and there you go. The TX part, it's what I said, a clock and data. You have to take care that your data is available. You put the data available on the low-going edge, and it will be sent out on the rising edge. RX, it's the way around. The data will be present, it will be valid on the rising edge, and changes on the falling edge. Yeah. So for such a small controller, again, 16 megahertz, I have, in case of DMR and fusion, 9,600 interrupts a second. That means 104 microseconds per interrupt with the speed of 16 megahertz and a 62.5 nanoseconds per single instruction. That is not all the instructions, because you have also 2 clock instructions. You have 1,664 single clock instructions per interrupt. That looks a lot, but if you see later on the tables, the Hamming tables and so on, it's squeezing. Fusion DMR again, 9,600 interrupts, and D-Star 4,800. The serial port handler. We communicate between the modem, the radio modem, and the host with 115K2. We have maximum 252 bytes payload because of the nature of the protocol. We agree to frame start with an E0, then specify the length of the message, including the frame start and the command or response type. So that defines the actually destination of the message. So these 3 command bits makes it that we have 252 bytes payload instead of 255. Standard format of the message. An example is that, for example, to set the modem in a particular mode, we have the frame start, a length of 4 bytes. It's a command type 3, and if you send a 1, then it switches to D-Star. Then the funny part is the DV protocol example. I take DMR as an example because it's a nice, clear protocol, and it has some difficulty to compare to D-Star. DMR, it's 4 FSK. 4 FSK mean every frequency switch you send 2 bits. If you go to a +1, +3, it always says something about 2 bits, a die bit. That's why we talk about 4,800 symbols a second. This is a symbol, which is 9,600 bits a second, because every symbol sets 2 bits. We work with TDMA, 2 time slots, 30 milliseconds per time slot, so you can have on one frequency 2 DMR conversations, 1 time slot 1, 1 time slot 2. Every time slot has 2,450 bits voice and 1,150 bits FEC in an AMBE packet, in the AMBE data. And there is 1200-bit embedded data added to. This is how a TDMA burst looks like. Two packages, 2 time slots, each in a frame of 30 milliseconds. In fact, they are 27.5 long in data. What you see is that the sync word and the embedded signaling is in the middle. And we are not used to that because packet radio all starts with the preamble, a sync word, and then we are used to send data. DMR is not doing that because of the TDMA nature. The data, left and right from the sync pulse, has no further preambling or triggering or whatsoever. The first symbol, in other words, the first 2 bits, have to be spot on. And they aren't in 90% of the case because the internal data parallel has to sync every time, every 60 milliseconds, because one time slot is 30 milliseconds repeated every 60, which is the length of a TDMA frame. But the forward error correction is taking care for that system. The sync word is not protected by any FEC at all. So that's why it is in the middle there. We have the best chance to get the sync word. It's not decoded, it's not interleaved, it's one sync word. Another typical thing of the sync word is that it is only 57DF. And that are the 2 outer deviations of the 4 FSK. If you have a +3, -3, then you have a 7. If you have a -3, a +3, then you have 1101, which is a D. If you have a -3, -3, then you have F. If you have a +3, +3, then you have a 5. So the sync word is always the 2 outer steps of the 4 FSK. So we have the sync. In this part, we can put some slow data, some ID information, but I come to that in the next sheets. And left and right is a payload, most of the time the voice. Voice initiation. So you press your mic. What's going to happen digital-wise? There will be sent 1, most of the times 3 to 5 link control headers. In this packet, there is information about your destination ID, is to which talk group you want to talk to, and your source ID, who am I? You have to announce yourself on a digital network. Then you have voice frames, and the voice frames are collected in packages of 6, and that they call a voice super frame. The first package has a real sync word, uncoded, uninterleaved, nothing. You can sync on that word. The other have the same information as in the link control header, but spread over 4 bytes. But I come to that. Most important is that you have 6 frames, which they call a voice super frame. And that's repeated every time. So, for example, when you miss the header, the system can check the 4 frames after a sync word, and that's what they call a late entry. Again, the voice super frame, and if you release your mic, there's coming another data packet, and that says this is the end of the transmission. The link control header is the first package is sent after you've pressed the mic. It has information, and that's the full LC. It means it's your color code. The color code is something like a CSS code, but then digital in your stream. If you have two repeaters, not so quite close together, but with good conditions, they can hear each other, or at least you're as a station in the middle of the two can hear them. Then one repeater has color code 1, the other 2, for example, and that's why how you can distinguish them in situation with good conditions. Again, it's the color code, the data type. The data type is a 4-bit code that says something about what kind of data. Is it a voice data header, or is it data, or is the terminator? That's in this one. These are not included in the embedded signaling because of the fact that when you listen, you have to do decoding very quickly. And if you put everything under the same forward error correction tables, and you will see how complicated they can be, then it's a waste of processor time. If you want to listen to a particular color code, then you can check on these bits, provided with also FEC parity, then you can do a quick calculation on that. This is the same frame, the information, slot type, and the sync or the LC. You have 72 bits data. You see them in a table later. It's your, again, destination ID, your source ID, some other bits and bytes. Provided with a 24-bit CRC that is going into a block product turbo coder, which makes from the 96 bits 196. And again, I'll show you later the table how that's done. That's going into an interleaver, and it's placed in the payload, left and right of the center. The interleaver is always used in digital communication to spread the risk when 2 bits are disturbed RF-wise. The chance is very, very big that they not after each other in the decoded data because of the interleaved format. So the 70, I can show it here. The first one, the 72 bits, is this table. You have a protection flag. Some bits are reserved. There are a lot of bits in DMR not used, at least in the area where we as ham radio amateurs use DMR. FLCO says something about the data in this block and a future ID set, which is not used at the moment, same as the service options. Most important things we use is the target address, that is your destination ID, and the source address, it's your own ID. Very simple. If you have, for example, talk group 204, you translate 204 decimal to a 24-bit digital code, put it in here, and that is how it's sent. LC data, including 24-bit CRC, is 9, including 3 bytes, 12 bytes. The 12 bytes are represented here and are put in a table over here. So we start with I-95, I-95, and fill the table like that. Because of the fact that the total numbers of location in this table is not the same as 12 bytes, we have 3 filler bits which are 0. Then you're going to do humming. Humming is a FEC protection mechanism where you do a calculation on these 11 bits and put the result here. You do a different calculation in another order and put it here. Now, how more humming bits you have here, how more you can, now how better you can see which bit is eventually broken. It's done. Again, the data is in here. The humming is calculated horizontally and vertically. As an example, the first row, this is the data with the 3 fillers, but in fact it's the same for the second row. What you do, the first bit is an exclusive OR operation of R210 95. Hey, it's upside down.
Or backwards.
Hey, that's funny. Is it upside down? No, it's strange, but okay.
It's mirrored. Mirrored.
Yeah, here also?
Right here, upside down there.
Yeah. Strange.
Oh, you're right. It's upside down.
Yeah, but okay, never mind. It's an XOR operation of these bits. For example, if the first one, which is bit R2, if it's broken, then you receive this from RF, put it in memory, and you read the humming bits here. Then you're going to do a recalculation of the data, and you do the recalculation according to this table. Then you have 4 new bits. If these bits are exactly the same as these, so if you XOR these with these bits and you come to 0, then your data is received okay. If you have, for example, a 1001, yeah, I said it right, 1001, then bit 1 is broken because R2 is in this collection, is not in this collection, not in this one, and is in this collection. So the XOR operation of these 2 calculations will fail. So if your result of the received Hamming bits and the recalculated Hamming bits is 1001, then you know my first bit is broken. It can be the situation that 2 bits are broken. No problem, I do not know all the tables out of the top of my head, but you start repairing the first you see, and you do it not more than 4 times. You recalculate 4 times until, not until, you repeat it until you have a 0 or a maximum of 4 times. That's how data will be repaired until a certain amount of broken bits. Then the interleaver, if we place all the bits in a row, send them to RF, and there is a radio disturbance, there are 3 bits broken, 9 out of 10 that the 3 bits are in one row. If you have the humming situation, you can handle a maximum of 4 bits. So you have to take care that the bits, which are digitally in a row, are spread out over, are spread out over the spectrum. So that's what you do with a, they call that a modulo 181. That means that the first bit you place on position 0. The second one at 181. The third one is 181 plus 181 minus 196, and 196 is the max table. So that's how they actually, they are always 181 positions from each other. So a voice header in terms of bits looks like this. In the middle, you have the sync words, you have the slot type, the R, the humming bits, and the information bits. Of course, when you want to read it out, you have to go the way back to the 72 bits where you can read destination and source. A voice superframe, and now I'm going to explain what the EMB, the embedded signaling, is doing, because I only spoke digital-wise now about the header. But if you have a double with someone, or the 3, maybe 4 headers are not received correctly, then it can be the case that your transmission can go to the network. Then we have a mechanism in that on the flow, the system can read the data from the embedded signaling, and we put the same data as in the header, your destination, your source ID, spread over 4 voice frames. So that means that if you have a double, the other station releases the mic, it sees, hey, I see a sync word, I can read the embedded signaling, and I still know again what destination do you have entered, and who are you? The A-frame has 260-bit voice left and right, and 48-bit sync to know that it is a voice sync word, and B till F has 260 voice left and right and embedded signaling. The voice left and right is 108 bits. Added together, 216. If you divide 216 by 3, then you come on a number of 72. And 72 bits is exactly the size of a AMBE packet, which has to be sent or received from the AMBE every 20 milliseconds. So, and that fits nice if you do a quick calculation of a frame of 30 milliseconds, but in the 30 milliseconds you have to provide also the voice data of the next 30 milliseconds that your radio is silent. Because with 30 milliseconds you have to fill a time of 60. Again, 3 MB packages of 20 milliseconds is 60 milliseconds. So that quick calculation proves that the data here can continuously feed the MB. So frame A has a sync word, and frame B until frame F has the EMB embedded signaling. This is the EMB, and that's repetitive for all the frames B till F. The only difference is the LCSS. That is a code that says this is the first one. 01 says there's coming another one, and 10 says I'm the last one. Embedded signaling is that one which is important for late entry. Again, we know the 72 bits. This time it's not provided with the 24-bit CRC, but with the 5 bits CRC check. Why? The header is sent only once, at least 1 time a pass. And this one is repeated every 300 milliseconds. So if it's not so well protected or the FEC is not so strong as a data header, is no problem, because the next voice superframe is coming within 360 milliseconds. So again, here we have the same with one difference, is that here are the 72 bits. Here we have the 5 CRC bits, humming horizontal, not 4 but 5 bits this time. And vertically, in the header is vertically humming done as well. And here it's only a parity bit. To do a quick check, is my data valid? Because if you check, is my data valid here? Is my CRC okay? Then you don't have to go into all the Hamming stuff. It's interleaved in a different way this time. It's spread over 4 bursts. And that's 1, 2, 3, 4. Actually, when you want to read the complete LC, you have to read at least 1 voice superframe, extract the 4 embedded signalings, go via this table to the uncoded data. And the last one is a null. Only nulls are in that one. Voice has no additional FEC. Now we have nice systems to protect data, color codes, everything. Only the voice not. Why? The 72 bits that are sent to the MB have already FEC. I told you it's 3600 bits a second, and you have 2450 bits voice data, 1150 FEC. Inside the MB you find same systems, also Galway Hamming stuff, interleaving. At the end it's more or less the same. That's why, no, that's not why, but we do not do any more FEC interleaving on the voice because it's done in the data itself. That's why you see voice 2, 25, 14, it's numbered in a row. The development at this moment, I don't know, I know at least 2 guys who were in Orlando 6 weeks ago, saw the new radio. So the dongle is the MB board with a carrier. A carrier, it's nothing more than a TTL USB converter to code digital streams, go PCM in and get DMR fusion or D-star back. That one. The funny IP radio, so it's, as Scott mentioned, a radio with no radio. I asked some people there, do you know a D-star repeater which is not connected to a reflector at all, a standalone D-star repeater? Now, there were not so many people that knew a standalone D-star repeater. Okay, then you work also with hotspots. The hotspot is connected to a reflector, the repeater is connected to, you can talk via a hotspot to a reflector and vice versa. And I had the radio there on the table with the microphone connected. And I said, how many times are you further away with your radio from your hotspot than the length of the microphone cable? So, yeah, you know where I want to go to. So, the IP radio, I think it will not replace the radios, of course not. But we deal now with three big modes, DMR, D-star, fusion, but don't forget P25, NXDN, and there are another 2 which I don't have at the top of my head now. But so this guy has a own main board based on STM32, communicates with the MB3000. The protocols are made inside the radio, so the data which is coming out is compatible, complies all the standards, whether it's D-star, DMR, or fusion. And we have a small socket in where you can place different boards. You can place a USB TTL converter to use an external host software, for example, MMDVM host, BlueDV, Are there more? I don't know. We can put a NanoPi Raspberry. Oh, no, that's not Raspberry. It's a NanoPi Neo. So it's a small board where the MDVM host can run on, and then it's completely standalone. You connect your internet of your network cable or a Wi-Fi dongle, makes no sense. 2.4 next-gen touchscreen to set as GUI to enter the talk group. You want to go to link in case of D-Star. New thing that I agreed with Jonathan, the maker of MDVM host last week, is that there will be a transparent communication channel available through MMDVM host. That means he has a UDP port where a third party can send a command to. That command will be packed, will be framed in MMDVM protocol and sent to the modem. So that makes us unit makers, module makers, possible to communicate via the screen to a app on the Raspberry. Before that wasn't impossible because there was only one communication channel to MMDVM host, and it was a serial port. And since you cannot use one serial port with two applications, you had to find something. So Jonathan built a command tunnel through MMDVM host. The DV Mega cast. The DV Mega Handy, I don't have any picture at all because I have to start a project, but that will be this one. In a handheld, you have to think about a Titera 380. Remove the keypad, extend the display. It will be a display like this, touchscreen. I hope to start in August, September with that one. And this is also a new board. It's a standalone DV host based on an ESP32. Yeah, what you see here is an 8266, but I've ported the firmware already, but I had the picture with a nice done board, factory done board with that. But you don't need BlueDV anymore, you don't need MMDVM host anymore. You take this board, provide it with Wi-Fi. The interface is, let's say I was inspired by Google Chromecast. You power up your unit, it cannot connect to a network, it turns into an access point. You can use your a wireless device, whether it's a phone or a tablet, to connect the DV Mega host to a Wi-Fi network. It sees Wi-Fi, it turns into a web server where you can configure your host, enter your call sign, your whatever. The standard DV Mega, and I also talk about the DV Mega from 2013-14, will fit and function on this board. So then you have a small stack size of a matchbox with everything in. At this moment, the firmware is ready for DMR, and as soon as this one is running in production, we have received the boards, Metalworks in 1-2 weeks, then I continue with the other modes in that board. From the Netherlands. Any questions? The Swiss, yeah. Yeah, but the Swiss Army knife is much more known as the Dutch DV Mega. But I do my best. Thank you.
Any questions? Yeah, sorry, did we burn your eyeballs? No questions. Yeah.
Question about consumer beware. So now there's Zoom Spot, Jumbo Spot, Shark RF, DV Mega. From your non-biased perspective, what should the consumer beware of with all the options when we're looking for a DMR hotspot?
Yeah, I don't want to be biased and don't say what you have to buy, but I can mention some differences. And if you buy, for example, a board made in China, there is no import taxes, VAT. There is no care taken for a bit of margin for eventual a reseller, like Gigaparts, Wemo in Germany. So if you want to have support, continuity, knowing that all the financial things like import tax, VAT, everything is taken care for, you buy from a local reseller, a dealer. And if you buy a board in China, there is absolutely no space for any dealer profit at all. So building a network with no margin is quite difficult. And we have now 18 resellers worldwide. You can find them on the website. And yeah, they are having stock, they are taking care for continuity, answering questions. That is the difference I can mention. Furthermore, the hardware is all based, and there I have to be honest, on the ADF 7021. The only difference in the modem itself is that all the ZumSpot types, MMDVM hotspot heads, are running on a firmware derived from Jonathan's work, G4K Lix MMDVM multi-mode modem, which is not bad at all, but it's the same firmware. I have my own firmware in the controller. There's a difference. No thanks.
Steve, here you go.
You mentioned in passing P25 and NXDN. Any plans to support those?
Yes. P25, I received my radio 2 weeks ago. Forgot the name. A guy here in the US helped me to buy someone because in Europe, in the Netherlands, you don't find a P25 radio at all. So he helped me to buy one. I have a Motorola X3000 something, and I start implementing P25. I have only a bit of space in the Atmega 328, but the DV Mega is talking two protocols. The old PCP2 protocol to the D-Star repeater software from Jonathan and a new MMDVM host. Since P25 and also DMR and Fusion is not supported by the old software from Jonathan, the PCP2 protocol, I skip that protocol in new version, and then I have enough space to put P25 in. So it makes no sense to have PCP2 in that case anyway. So yes, and I start with that very soon.
There's another European digital voice standard, Tetra, as
Tetra, yeah. Tetra is different. It has, I believe, 4 or 6 time slots. We cannot use it because of the occupied bandwidth. We are not allowed at this moment to do 25 kilohertz voice. So, yeah, some people are playing with it, but yeah, repeaters building is difficult. But we thought that also in the beginning of DMR, we can never make DMR, but we did it. So, yeah. We know it. Some people, I think in the Netherlands, is 1 or 2 experimental Tetra repeaters.
Oh, hi. I just have a quick question about how do you get around the licensing problems? Like, isn't Tetra proprietary?
D-Star is free. Protocol is free. Fusion is so far free. DMR is an open standard to read, but is not free to use. And I did what they proposed. If you want to develop some hardware where our protocol is involved, please make a call. And I did. I spoke for 45 minutes with one of their lawyers, and I have nothing in written, but nobody has anything in written until you pay them. But I'm allowed to use until 2,000-3,000 pieces a year, and they ask me when I go over the 3,000 that they want me to be as honest as I was to asking the first time to come back to them. So at this moment, no licensing problem.
Well, thank you very much.
Yeah.
We'll have to put the schedule back up here, but I believe we have a break for 15 minutes or so, and we will have tours to the restrooms leaving shortly. All right, let's go ahead and get started again. I tried. My printer refused to print I had a little sheet with all everybody's bios on it, and my printer just refused. All right, let's go ahead and get started. They're trickling in. Still see quite a few empty seats, though. Maybe that's an idea. There we go. Isn't the switch on the top? I think it's right there on the top. Yeah, that's good. Uh-oh. All right. Let's go ahead and get started. And our next speaker here is John Langner, WB2OSZ, got his ham license in high school. His interests include specialty communications modes such as RIDI, packet radio, SSTV, and APRS. John also loves to tinker. John has been published in Byte, 73, ham radio, and QST. John also developed software and had jobs in information technology. He will be talking about his Direwolf software that he developed and why you should never use a hardware TNC again, right? Please welcome John.
Okay, thanks, Scott.
You need to get
it's
you
an
up
honor
here.
to be here. Nope.
Wrong one. Wrong presentation.
Wrong show.
It's a Mac.
Yep, much better. Great. Oops, back up. Okay, so today I'm going to be talking about the Direwolf software TNC. Can you hear me okay? No? Seem to be turned on.
Yeah, I think it's a location thing and not a. Is that better? Talk
Is this
now.
better? No? No?
Really? You need to.
I can
speak up
shout.
then. Yep.
I can hear an echo.
Yep. There you go. We're getting
You're okay now? No?
I hear the echo in the room.
I can hear an echo, so it's being picked up, but
Yep. That's on. Let's try. Mike's hot, so I can hear that. Try that.
hello? Hello? No?
Just speak a little louder.
Is it okay if I speak a lot louder? That good? Okay, I'll just have to shout. Okay, so before we talk about getting rid of the TNC, I want to back up a little bit and first do a little bit of terminology and concepts. First, what is a TNC? Then we'll talk about getting rid of it. I'd like to talk a little bit about the challenges in building a demodulator. That was the most interesting part. APRS TT. And if we have time left over, I'll talk a little bit about the improvements in the AX.25 protocol version 2.2 that makes it better for moving large amounts of information. First, a little poll. How many people are familiar with traditional packet radio or APRS? It's pretty much, like 90%. How many people are already familiar with the Direwolf software? Maybe half? no, less than half, maybe 40%. Okay. And how many people know about APRS-TT? 3. Okay, good. So there will be some new material here for just about everyone. So back when I got started in ham radio, this is how we sent text. Okay? This is actually a picture from my ham radio club in high school. And these teletype machines were developed in the 1930s, and as soon as they became available in the surplus market, hams put them on the radio, and radio plus teletype is ready. It was pretty easy to get started. You just built up a simple modem called a terminal unit, fed it into your transmitter, and off you go. But it wasn't very satisfactory. You'd flip on your transmitter, it would be sitting there 100% duty cycle, doing nothing, and you'd press a key, and it would just send out, you know, one key or one character at a time. There's no error checking. Not very effective. So around 1978, some hams in Vancouver came up with a radical new way of sending data over ham radio. They called it packet radio because the information was sent in small packets or packages. And each transmission started, I guess it works better if yeah, it doesn't work so good if I go this way. It's better this way. So each transmission begins with a certain pattern called a flag that cannot occur within the data. You then have some addresses, like the station it came from, where it's going to, possibly repeaters. There's control information that tells the type of packet, the information part, the actual useful data. And then there's the frame check sequence, which uses a cyclic redundancy check. And the idea here is that all the earlier bits are put through a mathematical process with shifting and exclusive ORing, and it comes up with a 16-bit number. And if the data gets corrupted, that number will not match up. Okay, it's computed at the transmit end, recomputed at the receive end, and that 16-bit number should match. If it doesn't, something got corrupted, and we just throw it away. So the way this was implemented is they had to put some brains in front of the modem. Okay, that's a brain there from the PowerPoint clip art collection. And so adding a microprocessor in front of the modem was then known as a terminal node controller, or TNC. And the original usage back then is people would have dumb terminals. They would talk to the TNC. You could compose an entire line of information, hit enter, and then it would get blasted out as a short packet, you know, rather than tying up the channel for a long time. There are many advantages to this. Instead of turning the transmitter on and letting it sit there, it just sends out a short burst, gets out of the way. Each transmission has addresses of where it's coming from, where it's going to. This allows many people to share the same channel. There's error detection, so you know if the data got there properly. The higher level protocol allowed the TNC to gather up many lines of data, send them, do retries, acknowledgments, and get the information there successfully, or report that it didn't get there. And it was also transparent in that you could send any arbitrary data, not just text. You could send, say, a JPEG picture file. The Vancouver approach got things going, but they only from what I've read, they only made bare boards available. So that was not very convenient. People had to gather up all the parts, and it was a lot of work. And a few years later, the Tucson Amateur Packet Radio produced a complete kit. Here's the Tapper TNC-1. So the kit came with everything except the case. It was about $350, and this made it a lot easier for people to get started. But they throw an enormous amount of hardware at it. There's like 27 chips in there. There's an HDC controller that was something like $30 or $40, and that could have been done very easily in software. So to make a long story short, they came out with a newer model a few years later. Other manufacturers came up with products, and packet radio was pretty hot for a little while. So the TNC was designed with a dumb terminal in mind. Don't pay attention to the specifics here, but the main point is when you send information to the TNC, you might be sending it commands or you might be sending it data for it to be transmitted, and that depends on the current state. Or when information comes back from the TNC, it could be just monitoring of what's going on in the channel. It could be communication from a specific station that you're connected to. Could be changes in status, could be responses to commands. So it's not a real good interface for a computer, like if you were doing a bulletin board system or something like that. So this led to the KISS interface, right? What does KISS stand for? All right, simple. It was very simple. Now the personal computer builds up the packet to be transmitted, sends it to the TNC, and all that the TNC does is it puts it into an HDLC frame. Right, so here on the left, we have all the addresses, data, and everything. Send it to the TNC over an RS-232 line, and it just adds the flags and the frame check sequence. So that's all pretty simple. And this also opens a new market in that you can make a much cheaper TNC with much simpler software and less memory because it doesn't have to do much. So packet radio thrived for a little while, and then like in the later 90s, it kind of faded out, probably because the internet became available and we started using bulletin boards there rather than the radio. So along comes APRS, like late 1990s, and instead of connecting to one specific station, it's now more of a general broadcast. And while many people think of APRS as simply tracking cars moving around or houses saying, I'm still here, I haven't moved, I'm still here, if you've listened to APRS, like 90% of it is, this house hasn't moved, this house hasn't moved. But you can do a lot more with it. There are a lot of weather stations. A lot of people have home weather stations and transmit the data, so this can all be aggregated even if the internet is out. Telemetry can be used to send any sort of arbitrary data, and it has provisions for labels and units. You can direct messages to specific people or send bulletins to groups. And there's ways to send queries and get responses. So when APRS got started, we used the old TNCs from the 1980s. But we now have these personal computers that have a lot more power. So why spend $200 on something from the 1980s and put it in the middle? You can just eliminate that, and the radio can go straight to the radio. It's cheaper. You can get better results. It's easier to make updates. Instead of just download new software instead of replacing ROMs. So that brings us to our main topic. What's Direwolf? This is software that can be used to replace the traditional TNC. It's open source. It's free. It's portable. It runs on Windows. Runs on Linux. Works on x86 or ARM processors. So it can works on the Raspberry Pi. Oh yeah, even Macintosh. without, I don't have one, but people in the community, came up with the necessary adjustments and build procedures. It does work. Without adding any additional software, you can add a GPS receiver. It becomes a tracker. It can be a digital repeater, a gateway which talks to other gateways over the internet, well, not directly through servers and then to other gateways. And it can be used for APR STT, which 3 people knew about, and I'll get into that. And of course, it could be used as a virtual TNC for other applications that were written to use a hardware TNC. So, where'd the name come from? I was just juggling different words around and accidentally fell upon this combination. And of course, direwolf is an actual extinct animal, so the name is used for other things, mostly in video games, so there shouldn't be any confusion there. So here we have an outline of all the different functionality. And we now have the outline on the right side, so as I go into each one of these little topics, you'll see how it fits into the big picture. Of course, the interface to the radios is audio. Okay, many different types of audio interfaces here. The original sound card, and we still use the term sound card even though they're not cards. The signal link USB. Okay, I'll back up a bit. So the audio is pretty straightforward, but the push-to-talk is always problematic. How do you tell the transmitter to turn on and off? In the early days, you'd use one of the status lines from an RS-232 port, but those are extinct now. The signal link USB has a Vox circuit, so it turns on the transmitter automatically when there's transmit audio present and drops the transmitter when it disappears. If we're using a single board computer like the Raspberry Pi, there's plenty of general purpose I/O pins available that we can use for push to talk. And here we have the UDRC, which is basically just a sound card. It was originally designed for digital voice, but it works fine in this application. And finally, lower left, this is a USB audio adapter. They run like $5 to $10. Just pop it into the USB port, and it has microphone input and headphone output. And you might notice this little wire here. I don't know how visible it is from back there. But I drilled a hole in the case, and it turns out that the most common chips have extra general purpose I/O lines available. Okay, so in some commercial products, they might be used for indicator lights or push buttons, volume up, down, whatever, but we can use that general purpose I/O for the push to talk signal. And there's actually 3 different commercial products already that use that technique. So that's a very tidy solution. You get your audio and push to talk through one USB connection. For software-defined radio, there's different ways we can get the information in there. Again, along the bottom, we have 1200 baud modem, which is the most common. And I find it interesting to note that the AX.25 standard for packet radio says absolutely nothing about the modem. Okay, modem's not mentioned anywhere. But the Vancouver group started using the Bell 202 because they got their hands on a big pile of old modems for almost for free. And here we are 40 years later using the same thing. And we'll get back to this later. For 9600 baud, This is excitement back there. It's 4 times as fast. People were doing this in the late 1980s, so it's nothing new. Except back then, it was done with lots of hardware, and now we can just take the signal from the discriminator, put it in the computer, do it all in software. But the thing you have to watch out for is it requires a lot of bandwidth, about 5 kilohertz. So if you try using the microphone and speaker connections, it's not going to work. Okay, now we're getting into some other features that you wouldn't find in the hardware TNCs. Direwolf also has a touch tone decoder. So you can receive touch tones. It gets packaged up into a packet format that then gets passed up to the higher level here, to these other functions that process the received packets. So somebody could send a touch tone sequence, terminate it with a pound sign, and you could then write your own application that would process that and do something with it. In the opposite direction, all you need to do is, if you put DTMF in the destination address, instead of sending out an AX.25 packet, it'll send it out as touch tones. And it also has the ability to send speech. It doesn't have a built-in speech synthesizer, but if you put the letters speech in the destination, it runs a user-supplied script, and then that script can invoke a speech synthesizer. And it'll send Morse code. Okay, again, just put Morse in the destination, and it'll send it as Morse code. Okay, so we're talking about the lower half here, ways of communicating with the radio. And now we're in the upper half. These functions either process the received packets or create new packets to be transmitted. So beacons, of course, are things that you just transmit. You might put the location of your house there. If you get the location from a GPS receiver, you then have a tracker. It's all very flexible. Instead of sending fixed format information, beacons can also invoke a user-defined script. So that'll run, you produce whatever information you want, and then that gets transmitted. So that's useful for things like weather stations or telemetry. Direwolf also comes with what I call the Telemetry Toolkit. This is some documentation and scripts and sample code that allows you to measure quantities and then send information over the radio. And there's even an example in there of taking an analog to digital converter, hooking it up to a Raspberry Pi, measuring a voltage, and then transmitting it over the radio. But it's just a toolkit. It's not a turnkey solution. It's just a start for you to do your own custom application. There's also an APRS-TT gateway, and what that does is back up. And it takes, uses the touch-tone decoder down here somewhere. The information gets sent into the APRS-TT gateway. Oh, yeah, you can't hear me here. You can hear me here, so I can't, I gotta turn. That would be too easy. And we'll get into these details later. This is just an overview. Oh, so it receives the touch tones, and then it can send either voice or Morse code as a response. Okay, is this better? Not much. That's okay. I can just do this. Break that. Break for a drink. Okay, how's that? Nope, it's still not good here, but that's okay. We can work around this. Direwolf also contains a digital repeater. Now, voice repeaters, analog voice repeaters, listen on one channel and then simultaneously transmit the same thing on a different frequency. But here, a digital repeater receives the complete packet, stores it in memory, looks at it, figures out what to do about it, and will generally retransmit on the same frequency. But Direwolf has the ability to talk to several radios at the same time, so it's possible to do, say, like crossband repeating between different channels. And there's all sorts of filtering in there, so you can restrict what gets repeated. Like if there's some annoying operator, you can say don't retransmit anything from the station. The internet gateway is used to connect disjoint radio networks. And I think many people are familiar with the case where the local iGate picks up something from the radio, sends it up to the servers, and then you look at it on aprs.fi or findu.com. But it's really meant to be a two-way system. So say Ham1 could send a message to his friend, anywhere in the world. It goes into the local iGate. It gets sent up to the APRS servers. The servers then say, well, where have we heard Ham2 recently? And then the servers send the message to possibly several iGate stations near where Ham2 has been heard recently. Then Ham2 receives the message, and then the station automatically sends. That's not working. It's making noise. Then that station automatically sends an acknowledgement, goes through one or more iGates off to the servers, and then the same thing, it says, where was Ham1 heard recently? And then the acknowledgement gets returned so you know that the message was delivered. So many people set up receive-only iGates, but that's really like crippling the grand vision. That should be a two-way system to link. Again, the idea is to link together disjoint radio networks rather than just putting everything on aprs.fi. Now, the hardware TNCs just had an RS-232 port, but now since we're using a computer, we have many other ways to talk to our applications. We have TCP/IP through Wi-Fi or Ethernet. We have Bluetooth. And we also have the advantage that we can talk to many different applications at the same time. So now I'd like to talk a little bit about the challenges of making a demodulator work with real-world signals. Here's a pretty good-looking APRS signal. On the left, we can see it's a lower tone. It shifts to a higher tone, shifts to a lower tone again. So it's called audio frequency shift keying, very simple, very primitive. So the challenge then becomes, which tone are we listening to? The higher tone or the lower tone? And one way of doing this, there are others, is you might have bandpass filters for the two frequencies, take the amplitude of each signal, do some low-pass filtering so the data can get through but not the original audio carrier, and then say which of these is stronger. So that works great on a perfect signal, like we just saw, where they're both the same amplitude. Yeah, there's different ways to implement this. Back in the old days, you might use inductors and capacitors. Later on, we'd use active filters. You can do the same thing in software. I have no academic or professional background in DSP, so it was a matter of a lot of reading, a lot of experimenting, trying different things, a lot of tweaking until it worked better. So after a lot of experimenting, I got it to decode perfect signals, patted myself on the back, good job. And then I started listening to real stuff over the radio, and guess what? Didn't work so well. So then I discovered this this TNC test CD that was constructed by WA8LMF. And what he did is he recorded a bunch of signals while driving around Los Angeles during rush hour. So it was total chaos, okay? You know, everybody piling on top of each other, all sorts of different devices. It was wonderful. And this is an important distinction right here, track 1 and track 2. On track 1, he took the signal straight from the discriminator of a receiver, so it was nice and flat, okay? Different, well, flat audio, flat response, wide bandwidth. He then ran it through a low-pass filter to simulate the effect of the de-emphasis used in most receivers. Now, I'll be getting into that. And this has pretty much become the de facto standard. People don't talk about signal-to-noise ratio or bit error rates or any of that. If you want to evaluate TNC performance, you take this CD and you see how well your TNC does with it. So many people have tested, many TNCs and software, and they've mentioned how many packets are decoded, and I've gathered them all together, and here are some of them. Columns don't line up. It must be a different version of PowerPoint that handles tabs differently. But anyhow, I've separated these. Well, first the disclaimer. This was done by different people, different times, different conditions. So don't take the numbers too seriously. Most people don't specify if they use track 1 or track 2. But when we put the numbers together, we do see a pattern here. The ones in yellow with the asterisk are the software implementations, and the ones in white are the hardware modem implementations. And when we plot this out, what we see are the hardware implementations usually get somewhere from the 700s to the upper 900s. And then along came the first generation of the software TNCs. They didn't do too well. Okay, one of them got 130. Another got about 500. Not so hot. So this gave the software TNC approach a bad reputation, and you'll find a whole lot of 10 and 15-year-old articles out there that say, for best results, you absolutely must buy a hardware TNC. Don't bother with a software approach. I'll get to you in a moment. But then there was later implementations did a lot better, and they leave the hardware modems behind. You had a quick question? This is 1200 baud, yeah. So, well, there's a lot of outdated information out there. I'll just leave it at that. So what I observed is that results from track 1 were a lot better than results from track 2. And in Direwolf, we have the audio level here. So the first number is the overall level as it's coming in from the very beginning. And then these, okay, technology. And then these two other numbers are the strengths of the two tones. So you can see in one case, they're the same strength. In another case, one is twice as strong as the other. So the explanation for this is the 1200 tone is a certain amplitude, and the 2200 hertz tone is half the amplitude, and that could be explained by having the low-pass filter that's decreasing the higher tone. And this is the reason for it. The voice transceivers are not designed for data. On the transmit end, we have something called pre-emphasis, where it boosts the higher frequencies. And then on the receive end, we have de-emphasis, where there's a low-pass filter that decreases the amplitude of the higher frequencies. In theory, it should balance out, but a lot of the time, they don't. So we end up with different situations. So in this case, if you look at the audio waveform, you can see that the lower frequency is much larger amplitude. And you could explain that because the transmitting end probably used flat audio, so they probably went straight into the modulator rather than going in through the microphone input, which would have the pre-emphasis. And then on the receive end, we have the de-emphasis that decreases the high frequency amplitude. Then we have the opposite case, where someone used the microphone input. And then, You're not supposed to look. You're not supposed to look at that. Just look at the shape. The clip art collection had one of the graphs and not the other, so I just like flipped it over. Don't look at the numbers. Just look at the shape. There's a couple other things I slipped over on you, but no one mentioned it. This is the opposite case. Opposite case, we have the pre-emphasis, the boosting of the higher frequency, but the receiver is flat audio, so you can see where the high frequency now has a larger amplitude and it's kind of spiky. Now, this messes up the comparison. You know, you want to know which one of these tones is stronger, but the radio is messing it up. So, this one is twice as strong, or this one's twice as strong, and the decode rate goes down. So, in my first experiment, I tried adding automatic gain control in there to compensate for it. And it worked. It had some improvement, but it was not ideal. And the next thing I tried doing was adding fixed gain and having multiple decoders, multiple HDLC decoders after that. And what I found is that when we use the original implementations, or the original signals through one decoder, it worked very well on track 1, which is, remember, the flat audio. And then I tried boosting the higher frequency and used a different decoder, and that worked a lot better on track 2. So what do? Well, you can run 2 of these in parallel, which raises the question, well, what are the best numbers to use in there? So I did a little study, and these are the number of packets decoded from each of the tracks, trying different gains. And it's kind of spread out. So what I ended up doing is running 9 of these in parallel with all sorts of different gains. It kind of overkill. Maybe 3, 4, 5 would work just as better, but I just total overkill. Because the earlier part of the demodulator is computationally intensive, but when we get down here, it doesn't take much processing power. So there's not much expense to doing a bunch of these at the same time. And over here on the right side in yellow, you see these little bars and underscores. A vertical bar means a packet was decoded successfully, no errors, and the underscore means nothing. So we can see we're running 9 decoders here. And on one signal, one set of them does real well. On a different signal, another set of them does real well. Give you a moment to read the words. So another experiment I thought I'd try doing is how many of the packets there have single bit errors, and could we do something about this? So instead of processing all the bits as they come in, I rewrote the code so it would look for the look for the start flag. It would gather up all the bits into a buffer. It would look for the end flag, and then we would go back and process it. Now, if the frame check sequence was not correct, I would then go through it and flip each one of the bits one at a time and recompute the frame check sequence and see and see if the frame check sequence was correct. Now, it's important that this is not forward error correction like others were talking about. Okay, we're not sending extra information that you can go fix it up to how it should be. This is just, it's not right. What can I do to make it appear to be right? It came up with a lot of false positives. Now, there's about 65,000 different combinations for the frame check sequence, but when you try hundreds of different combinations of flipping the bits around, you're going to run into a lot of false positives. So I added a sanity check to it. A valid AX.25 frame is going to have first it's going to be a multiple of 8 bits. I forgot to mention that. Addresses are 7 bits each, so the complete address part is going to be a multiple of 7, did I say bits? Bytes. There's going to be between 2 and 10 addresses, 7 bytes each. And if we know that we're dealing with APRS, we know what the control and protocol bytes are going to be. And the information part is going to be all printable characters or a few other special characters that are used. So by running it through the sanity check, we were pretty confident that we have something that's valid. Not 100%, but pretty good. So now we have a new score, but I don't put this into the comparison tables because it's cheating. Okay, we should only check, or we should only compare frames that are received correctly, no errors. But if you're using APRS, this will squeeze a few more out. Or maybe if you're using very weak signals from satellites, this could pay off. You don't want to use it if you're transferring important data. All right. Now, I call this the forgotten part of APRS. This is not a new idea. This came about, I think it was now 2002, where the father of APRS came up with this idea and did a prototype where he took a touch-tone decoder chip and hooked it up to the parallel port of a computer. Okay, this is going way back. And he wrote some software that would then take the tones and then change them into APRS packets and retransmit those. And this is the justification. Not too many people have portable equipment that have a built-in TNC, but almost everyone has an old HT that can generate touch tones. So this allows everybody to participate and put information into the APRS network. So this is the general idea. You have two radios. The first radio picks up the touch tones. The gateway then takes those tone sequences, converts them to an APRS packet and transmits it on another channel, and then it sends an acknowledgement to the original channel. This could be in Morse code or voice, saying, okay, I received the signal. Now the tone sequences are composed of one or more, I call them fields, where the fields are different types of information. And there's a certain pattern here where you have a field of different tones of, A, B, C, D, or the digits. Use the asterisk to separate the fields, and at the very end, you hit the pound sign. Now, fields beginning with A are used for call signs or objects and other attributes. A field beginning with B is used for location information. And there's several different ways of representing locations. For example, you might have a list of 10 fixed locations, and that could be represented by one digit. So that would be useful. Say you had some kind of race. You have start, a couple checkpoints along the way, and finish. There's the ability to have different types of grids based on either latitude and longitude and latitude, or UTM. But you wouldn't specify coordinates like anywhere in the world. Rather, you would define a local region, and then you'd specify a smaller number of digits within that region. A field beginning with C can be used for general comments, or there are specific cases, like if there's a single digit, you use a predefined table of different status, like en route, arrived, off duty, whatever. And D is mentioned as being for messages, but there was no definition of how that would be used, so I haven't implemented it. Now, you notice none of the fields in the original specification began with a digit, so I added my own little extension where you could have all short, all numeric fields, and then you could define what they mean. So using the original specification, you have horrible stuff like this. Yeah, okay, horrible. So the example here is you might have a bicycle race, and you wanted to say that bicycle number 123 is at location so-and-so, and we have an emergency situation. So horrible. No one's going to use this, okay? If you're out monitoring some event, you're not going to sit there and punch it in. It's ridiculous. So what I did is I came up with a way that you can define very short, numeric-only sequences for special cases. Okay, it requires no coding. You just put it in the configuration file. So you might say a field of exactly 3 digits would mean the first digit is one of 10 locations predefined. And then the other 2 digits would be an object number. So the object could be staff for the event, vehicles, participants, whatever. And this all goes in the configuration file. So if you were at checkpoint number 5 and canoe number 12 came down the river, you could just punch in 5, 12 pound, you're done. I have a little more complete example here for a hypothetical search and rescue event. And the scenario is that a bunch of people are called together very quickly to search for somebody lost in a park. And APRS trackers are not available, but someone wants to watch everybody's movements on a map. So what we can do is we can define a message format where 1 digit represents the team, and then we have 6 digits for the X and Y coordinates within a predefined region. So here's an example. We have the UTM coordinates, and luckily it works out that we can represent the east coordinate with 5 digits and the north coordinate with 5 digits. So that's how people can specify the location. So if you read from your GPS, that UTM location, you can then just pull out the 3 digits for the X, 3 digits for the Y, and just send those. So if the third team wanted to report their location, they'd just say 3, the east coordinate, the north coordinate, #, and that's all you need. And then right here, it appears on the map. Or for more complicated situations, you can use multiple fields. We would use the same 7-digit numeric field for the team number and location, and we could add extra things like a single digit might represent a status, and a C followed by 6 digits is the standard form for frequency. Oh, and I forgot to mention, after they transmit that, the APRS TT gateway responds in voice. So it might say team alpha at this location, subject found. Wow, yeah. So a few people have used this for some events. But I think it just needs a lot more publicity. I think it's a very powerful and useful concept. Just need a few more people to spread the word and give it a try. And so here we have Team A. In this particular application, if you click on the icon, it shows you the information like the frequency. And some applications, SAR-Track in this particular case, will show you information in tabular format. Okay, so that's APRS TT. We're a little tight on time, but I would like to very briefly mention a feature in AX.25 version 2.2 that makes it better for sending large amounts of information. First off, the original protocol restricted you to 256 bytes of information in a packet. Okay, after the addresses and everything, the actual useful data, it was restricted to 256 bytes. And in the later revision, there's no specific limit, and the two stations can negotiate. So one can say, I want to send 4K at a time, and the other sends back, no, I can only do 2K at a time. If you're acknowledging data, this is the stupid way of doing it, one at a time. So let's say the sending station sends 5 lines of data, right? The quick brown fox jumps. The TNC behind the scenes assigns sequence numbers. So it would send the first one. The receiving station says, okay, got it, ready for the next. You send one, okay, got it. Send another, okay, got it. This is very inefficient because each time you want to transmit something, you have to sit there, wait for the channel to be clear, wait a random amount of time so you don't step on to minimize the chances of stepping on other people. And then you have to usually turn on the transmitter, wait about 300 milliseconds, just sending filler information because it takes a while for the transmitter to stabilize and all that. So there's a lot of overhead in switching back and forth between transmit, receive. So this is the better way of doing it, and this is known as the window size. It's the number of packets that you can send before waiting for a response. So here we have 6 lines to send with a window size of 3. We turn on the transmitter once, blast out 3 packets all in one transmission, then turn off the transmitter. And the receiving end then says, okay, I got 3 of them. The sender sends 3 more. And this is a lot more efficient. So with the 2.2 revision, you have the option of using 7 bits instead of 3 bits for the sequence, which means you can have a much, much, much larger window size. You can send lots of stuff in one transmission before you wait for an acknowledgement. The other big improvement is the way you ask for resends. In the original protocol was written back in the days when we measured memory in kilobytes, but we don't do that anymore. So in this example, suppose we send 5 lines, and then the second one there is crossed out, meaning it gets clobbered by some sort of radio interference. So using the old protocol, only packet or frame 0 was received successfully. The receiving end says, well, the receiving end discards everything it wasn't expected in order and says, go back and start transmitting from number 1. So this is very inefficient. Even though frames 2, 3, and 4 got through successfully, the receiving end is so stupid, it didn't remember them. It just dropped them on the floor and says, start resending from 1. In the newer protocol, there's something called selective reject, and there's now a new command which asks only for those that were missed. So in this example, we blast out 5 packets. Numbers 1 and 3 got lost due to interference, and now the receiving end remembers the others and just says resend 1 and 3, and it puts everything in the proper order. So it's much more efficient. Now, unfortunately, this came out in 1998 when connected mode packet was on the decline. So what you find is most of the implementations were done before that time, and they never went back and updated it with these new features. And there are some partial implementations of this. I think mine's fairly complete. But I think the point I'm making is if you're moving large amounts of information, you might want to look at using the 2.2 protocol. Oh, and finally, the compatibility between the two of them. there are two different commands for establishing connections. So if you start with the newer protocol trying to make a connection, it would send a connect request using SABME. The E stands for extended addressing. If you have an older implementation, it says, I don't understand what you're talking about, and it sends back frame reject. In that case, the sending station then says, oh, you don't understand the newer protocol. It sends SABM, which is the older protocol, and then the older station says, oh, okay, that's cool. So it's very nice. If the older protocol, or if the station originating the connection uses the older protocol, it just works the old way. But if the newer implementation tries to connect, it fails and falls back. And that's it. I'm only 3 minutes over. That's it. Yes, not done yet.
I'm curious if you've done any implementation or thought about implementing the fabled FX.25.
I've read about it, and it's a cool idea. What it does is it takes, you have the original, I'll just talk about it. You have the original AX.25 frame, and then it puts forward error correction around it. So that we are sending extra information, I think, before and after. So a suitably equipped station could use that to properly fix errors instead of, like I did, just flip the bits and see if it works. I've read about it, but no, I haven't made any progress there. But the nice thing about it is you still have the original signal in the middle, so existing stations will just pick up that part, but the new stations, or the stations that understand the forward error correction, would use the whole thing. Is that a good explanation? Okay, I've read about it, but I haven't done anything in that direction.
And there were several things that you talked about that when there were several of us in this group that were running TCP/IP back in the day, and we would gut out our TNCs with KISS mode, and then the TCP/IP software would implement a lot of the protocol, and there was stuff in there that was way beyond us at the time, but now it's old hat. And does Direwolf do KISS?
Yeah,
Okay.
yeah, it implements KISS.
You mentioned the ability to support a 9600 BPS connection. There's some discussion around the possibility of some of us who are doing FSQ right now possibly adopting Direwolf and thereby getting additional modes open to us, including packet. And so my question is, a typical setup, Raspberry Pi, UDRC, FM radio with 6-pin interface, is that going to be capable of doing 9600 BPS?
Yes.
So it's not using an audio interface in that case, based on your comment?
Right. The big three radio manufacturers on some of the models have little 6-pin DIN connectors, and that has wideband audio suitable for 9600 baud.
So in the interest of getting people out of 1200 and into faster speeds, what's the best way to essentially, if you had, say, a UDRC equipped Pi type setup or any other Direwolf setup, to have it essentially decode, be able to talk at 1200, but also at one or two other speeds?
Okay. The software allows you to use a stereo sound card, and you can use different speeds on the left and right channels. And for receiving, it's okay, but on transmit, it'll only do one at a time. It's not smart enough to merge them. But my recommendation would be if you're running 2 radios to use 2 completely separate sound cards. The reason is each of the incoming, well, the reason is if you use 2 different sound cards, the decoders can run in 2 different threads. Well, they do run in they'll run in 2 different threads, and that'll take advantage of the multi-core processors that we have available now.
Okay, I have a few things, John, over here.
Oh, John.
To the point of the multi-speed, there is an experimental page on the UDRC group on groups.io. I have actually run multiple modems in parallel on the same sound stream coming in and out of a radio, and made it work. Actually had 1200 and 9600 on the same channel and just did it on a packet-by-packet basis. So it's possible, it's dangerous, you're going to irritate people if you don't know what you're doing, but it is there and it is possible. John, could you comment on your new duplex that's in 1.5, both for satellite, and could it be put into a true repeater mode? And also, you might want to mention some of the higher speeds that you've implemented in the modems.
Okay, yeah, version 1.5 will work in full duplex. Previously, it would transmit only if nothing was coming in. But of course, you'd have to use 2 different radio channels for that. But full duplex is there now. As for other speeds, some people challenged me to implement phase shift keying, and I just did it on a whim, not knowing what I did, and it seems to work. But I don't claim that I know what I'm doing. But if there are any modem experts out there, if you want to create extra modems, send them along. We'll integrate them in there.
I think you want to catch him at lunch? You want to be the last guy that holds everybody up, or we're welcome to. Just there's anyway. All right. So one more question.
One more.
So you're one of the very few that has actually given any thought at all to 9600 baud in using sound card devices. And from the reports I've heard from my buddies who really have dived in, it's a good implementation. How much interest are you seeing in 9600 baud now that it's getting a lot saner because you don't have to have a 9600 baud TNC?
Yeah, not enough. I've heard back from some people that they're using it, but I really can't gauge how much it's being used. But again, the challenge is you need the wide bandwidth audio. You just can't use the microphone and speaker connections.
So that's obviously one of the motivations here, right, is to show everybody how easily we can do this. So thank you for coming, John. So we have lunch break coming up. I forgot the time. We'll put it up on the screen. So if you want to head to the started 10 minutes ago, right. If you want to head to the bathrooms, any of these doors, go back toward the main doors, and we've got somebody waiting to let you in. Otherwise, if you want food, we have this last door here. Out the last door, you exit left, and there'll be 2 lines of food. There's 4 different kinds of sandwiches, right? There's ham, turkey, roast beef, and vegetarian. We have 2 full vegetarian ones, so for the 3 of you that are vegetarians, you have like feet of sandwich to eat. So anyway, feel free. Thanks, and we'll put a schedule up, and we'll see you in an hour or so.
Okay.
Questions?
Sure.
This is what I'm working on right now. I'm with a group in Blaine. We have a packet node. It's based on a TNC and an old PC.
we have maybe 3 people in the group of 30 who are capable of doing packet because they own TNCs as well. So I'm very excited I'm the sysop and I can't test my own node. So I'm very excited to pursue this.
So there's a fresh pot of coffee down here toward where the food is on this end of the
Turn this
room.
off.
So the far one's almost empty. The new one want to make a correction.
We do. This one's fuzzy and that one's not.
Oh, it is.
I thought it was just me.
Well, yeah, I was noticing.
It's also tilted.
You have to crawl up there and fix that.
There should be a key phrase.
All right, let's start going again here. Is there anyone out in the hallway we need to grab still? Now, who did that with the lights? That was cool. Oh, I see. There it is. I'm looking at this panel. There's no one even over there. 2 panels. How clever. Yeah. All right, so we have one more addition to our fabulous prizes here. Alex was kind enough to donate one of his LIF boards. So this is a device that you could install in on the IF of your radio, and it gives you a low frequency IF that you can then bring into your PC. So it basically allows you to get some SDR functionality out of your normal analog radio. So, thank you, Alex. Thank you. So, our next speaker. You ready here, Joe? Yep. Let me find my... So I have to say, I asked him for a bio when we first had some conversations, and he said, well, you can put together something off of the page, and it was his Nobel laureate page. And I was thinking, well, that's the first time that's ever happened. People often send me to some, Facebook thing or something, right? But not that. So Nobel laureate Joe Taylor, K1JT, first obtained his amateur radio license as a teenager, which led him to the field of radio astronomy. He is well known in the field of amateur weak signal communication. In 2010, he used the Arecibo radio telescope to conduct moon bounce with amateurs around the world using voice, Morse code, and digital communications. Joe Taylor shared the 1993 Nobel Prize in Physics for 30 years of observations of a binary pulsar that demonstrated the existence of gravitational radiation in the amount and with the properties first predicted by Albert Einstein. Joe's topic today is working the world with WSJT-X. That is what that says. Excellent. A software package and a protocol suite that utilizes computer-generated messages and radio transceivers to communicate over long distance. WSJT is useful for passing short messages via non-traditional radio communication methods such as moon bounce, meteor scatter, and other low signal-to-noise radio paths. It is useful for extremely long-distance contacts using very low power. So please welcome Dr. Joe Taylor.
Thank you, Scott, and it's great to be here with you, everybody. Sorry, my voice is a little bit off normal because of a cold, but I'm doing fine and really delighted to be with you. A good place to start this talk might be to emphasize the ways in which the kinds of digital communication I'll be talking about are different from the ones we've been hearing about this morning. In particular, we're at the opposite end of a spectrum in a sense, because the weak signal communication modes that I'll be talking about and that are implemented in this software program, WSJT-X, are made specifically for minimal contact, for making minimal contacts where you exchange call signs and signal reports and maybe a grid locator and not much else, as opposed to arbitrary information that you can exchange with digital voice or packet radio and so forth. So we're talking about cases where the signaling rate may be very much slower. The necessary signal-to-noise ratios are definitely very much lower. And in fact, the design goals of the various different modes implemented in WSJT-X and its forerunner program, which was simply called WSJT, are mainly VHF-oriented and VHF DXing. In particular, moon bounce and meteor scatter were two of the modes that motivated the development work that was done on these modes originally. So with that as a background, let's go ahead and let's see, the clicker here seems to work. Okay, so we're talking about a piece of that seemed to disappear, but I'm not sure why. The slide is mostly there, but there's that big blank area wasn't blank before. So starting from the top, I was sort of going through a history here of the development of these modes. They started out with a program that I called WSJT. The WS stood for weak signal. JT, of course, is just my call sign as well as my initials. And that started in 2001. The work started in 2001, where I was particularly interested in making something that would work well for meteor scatter on the VHF band, 6 and 2 meters in particular, but it also works a little bit higher in frequency. And moon bounce, which I was interested in doing. I had always been interested in doing it, and from my original ham radio time as a teenager back in the 1950s, when I wasn't able to achieve it, and then getting back into active ham radio 35 years later or so, near the turn of the century, I wanted to address that again. The second blank area on this slide referred to a program that I called MAP65, which was specifically for doing moon bounce on the 2 meter band particularly, but it's since then been used at higher frequencies as well. Basically, it's sort of the digital analog of using CW skimmer. Instead of decoding one signal that you tune to, it decodes a whole region of the band and decodes all the signals in there. And so you can find out, particularly, for example, during the annual ARRL EME contest, you can monitor the whole portion of the 2 meter band where the EME guys are working each other, and you can see who's calling CQ and who's ripe for a contact to add to your log. So that program implemented a number of new techniques, in particular multi-decoding like CW skimmer. You look at a whole lot of different signals, and adaptive polarization, because the linear polarization of signals that have been reflected from the moon and come back to the Earth through the Earth's ionosphere both ways have got their planes of polarization rotated by the Faraday rotation in the ionosphere, a magneto-ionic medium where you've got both ionized medium and a magnetic field. And that means that basically the angle at which linearly polarized signals will be received on Earth is arbitrary. You can't predict it from one hour to the next. It varies slowly as the line of sight through the ionosphere changes and the total amount of rotation changes. Then more recently, around 2008, the signal processing program known as WSPR, WSPR, turned out to be a nice acronym. And the letters stood for Weak Signal Propagation Reporter. And it in fact does whisper because most people use it with very low power, perhaps typical QRP power of 5 watts or so, but maybe only milliwatts. And with whisper signals, you can detect other signals and have yours detected anywhere in the world, typically with only a few milliwatts and a compromised antenna. It's fascinating that it works, but it does. And most recently, the program WSJT-X, which is mainly what I'm talking about today, brings together a lot of these concepts into one program. So this one is used at basically on all bands, many different modes, all the way from the new bands down below the broadcast band up to SHF bands, 10 and even 24 gigahertz. Moon bounce are being done typically with this program now. For various reasons, not least of which is the advent of the most recently added new mode in these programs, which is known as FT8. we've got now thousands of users worldwide. FT8 somehow caught the fancy of lots of users on the HF bands, and there are something like 15,000 users in any given week recently, which was a big surprise to us. You know, we weren't aiming for that kind of thing. We had a particular goal in mind when designing that mode. It had to do with working people on 6 meters during the summer sporadic E season when you get multiple hops, but typically the signals are weak and digitizing them makes it easier to dig them out of the noise. So I've been already using some jargon which may not be familiar to everybody here, and I just want to define a few terms to be sure we're all on the same page. When I'm talking about modes, I'm talking about a particular signaling protocol and signaling method and a protocol. You could call CW a mode, and PSK31 is certainly a popular digital mode, but the other ones that I'm talking about are ones that where the letters and numbers there strung out are the ones implemented in this program, WSJTX. They are all designed for making this minimal communication where you work somebody and put them in your log, you can add them to your DXCC total or your contest total, whatever it is, but you don't chew the rag. You don't exchange very much information beyond call signs, signal reports, locations, and so forth. So within these protocols, how do we define what makes one of them different from another one? Well, we're using different coding schemes, including all these modes, by the way, have FEC, forward error correction, built into them. They basically are very reliable. When you decode a message, it's error-free, or else the program simply gives you nothing. So you don't miscopy call signs or get a locator wrong and so forth. But the different modes use different forms of modulation. They use different symbol rates, different block sizes, and I'll go through a little bit of that as background, although the primary purpose of this talk was not to sort of give a designer's overview of the way the modes were designed and implemented. When I talk about codes, I'm mostly going to be talking about the error correcting codes built into each of these protocols. Broadly speaking, by a code we mean how some kind of symbols are going to represent information. And there are character by character modes that are widely used in ham radio, where you transmit one character at a time and build up words or numbers or whatever they are. Morse code is certainly an example, Baud is another, ASCII, and so forth. But the modes that we're going to be discussing here are all modes that are block structured. They have fixed length messages, a certain number of digital bits, and within that, the forward error correction scheme is an integral part. And we use various different FEC codes, partly because this whole thing was a learning exercise for me. I was looking for something new to play with and decided I wanted to learn communication theory. And so I've been experimenting with Reed-Solomon codes, convolutional codes, turbo codes, linear, low-density parity check codes, LDPC, that's what that stands for. The QRA or Query Repeat Accumulate codes most recently. All very fascinating, all fairly mathematical. And important to information theory or communication theory these days. So let me say a few things about why it is that all these different modes got built into WSJT and WSJTX. The X stood for experimental or extended or something like that when we brought that. I couldn't think of a better name, I guess, for the program. We could almost drop the X recently because it is the only program that people are using widely. I was aiming at making these minimal contacts between ham A and ham B work well under a variety of different propagation conditions. So certainly at MF and HF frequencies, we've got ground wave, we've got sky wave. As you go up in frequency, tropospheric scatter becomes an important possibility. When you're working on 2 meters out beyond 100 miles or so, you're getting into the troposcatter region. We were interested in multi-hop sporadic E. We were interested in moon bounce. That takes place almost exclusively on the VHF and UHF bands and up into the microwave bands. And certainly meteor scatter, aircraft scatter, ionospheric scatter, all of those things were interesting. And one of the ways in which these various modes are different is that the ones coded here in blue are ones that typically have fairly slow QSB or fading, and the depth of fading is relatively shallow. Whereas meteor scatter, for example, the depth is infinite, if you like. There's no signal there at all most of the time. And then for a brief instant, when there's a meteor shooting over somewhere in between station A and station B, you get a reflected or scattered signal which rises above the noise. And so very different techniques need to be used to exchange useful information in those brief amounts of time. Aircraft scatter has been becoming a much more interesting form of communication these days. For example, when you're working in a VHF, UHF contest and want to work guys out of the current local area, if you're on a path with a lot of overflying aircraft, you get good signals reflected from them, but only for a few seconds at a time. And if you can exchange the necessary contest information or whatever else it is that you're doing in those few seconds, you can work out to many hundreds of miles instead of just a fairly local region. So there you get the basic idea. So here are the various modes broken into two columns. Again, the blue ones are the ones that are particularly useful in slow fading conditions, and the scatter modes require different design goals in the protocols to make them work well. MSK 144 is currently the favorite mode for doing meteor scatter. There are some fast modes associated with the mode called JT9. In particular, JT9 with letters E through H after it. Their JT9 A, B, C, D have different spacings between the tones and different rates at which the tones are sent and so forth. On the right-hand side, the blue modes are all the slow ones. The one at the top, FT8, is the one that has been so extremely popular recently, and I'll talk in detail about that one. Whisper is down at the bottom. Whisper is different from all of these other modes in that it is not built to make two-way contact between stations. It's rather a sort of a quasi-beacon mode, or if you like, a one-way mode where you transmit now and then and receive most of the time and receive other stations, and reception reports are sent to a central database maintained by a different group, not by me, but at which you can basically see what paths are open worldwide. And that mode has been quite popular now for almost 10 years. By the way, before I go on into greater detail on any of these things, let's see a show of hands on people who have actually used WSJTX. Okay, so it's a fair few, probably less than half. And what about Whisper? Any Whisperers in here? Okay, some of those as well. Great. So just a few more words about why so many different modes. Again, it's because of different propagation types which have different characteristics which require different optimization schemes for making the protocol work most effectively. That means that the actual details of the code design and the optimization of various parameters that go into the protocol are different depending upon such things as the fading rate, the fading depth, the amount of Doppler spread on the signals. You send out a pure carrier. What gets received at the far end has got a little bit of wobble in the frequency caused by the nature of the propagation mechanism. And the receiver, for optimum decoding reliability, has to be able to allow for that, and so forth. Also, what was important under the why so many modes column is, again, the fact that I, and more recently we, speaking of the larger group which is now contributing to the development of this software, are people who are not necessarily trained experts in communication theory or DSP or any of the rest of it. We're learning as we go, and we try things and they work pretty well, and we make it part of the program and people use it, but then we find something that works even better. And so that's one of the other reasons why there are so many different modes. I might also mention, by the way, that as you might guess by my background, I don't necessarily approach these things quite the same way that a communications engineer would do. I tend to approach it from first principles as a physicist, and that means that I reinvent a lot of stuff that was already known by people in the communication field. And I do spend time in my university's engineering library reading the literature, but usually it's after I've already done whatever it was I was going to do. Then I find out, oh, well, they already knew that. Okay, so about mode design and the various different parameters that you might tune when you're doing this. All of these different modes use a block message structure, a fixed length block, which you try to communicate from A to B with no errors. Okay, that means that we typically use, the first thing that we typically do, starting with a human readable message that the transmitting operator wants to send to the other guy, you do compression. You compress that to the minimum number of bits that can be sort of a lossless form of compression, so that it can be decompressed at the other end back into the original message. So there's that kind of thing is referred to by communications engineers as source encoding. You take the source message and you encode it into the minimum number of bits. And then you add error control information. That's redundancy. That's forward error correction. And there are lots of different code types that are known. And we started out using ones that have been known for decades, like the Reed-Solomon code and various different convolutional codes. Most recently, we've been actually using things which are at the current forefront of the development of these kinds of things, including, for example, these low-density parity check codes, a very powerful way of encoding forward error correction information, which has been known since back around 1960-ish on paper, but which was completely impractical until we had very fast computers to do the decoding at the other end. But it's perfectly practical today, and we use it all the time. The information throughput rate has got to be part of the design. And once you sort of settle on the things in the top part of this list, you then have to choose a modulation type, a rate at which you're going to key the modulation, whether it's frequency shift keying or whatever. That means a signal rate. And those things together are going to turn out to define the occupied bandwidth of the signal. And in almost all cases, I think, the occupied bandwidths of the signals I'll be talking about are very small compared to the ones that we've been talking about earlier today. So we're not talking about taking many kilohertz of bandpass. It's typically a few hertz. FT8 signals are 50 hertz wide, and you can, that means you can jam a whole lot of them into the pass band of a typical single sideband transceiver. And you'll see more examples of that. One of them was on my title slide, where you saw about a 2 kilohertz slice of spectrum with 50 or so signals in it, all of which could be decoded independently. In all these cases, we're going to need an accurate synchronization method, synchronization between the timing of the frames of information and the individual symbols that make up the information in the frame. The receiver has got to resynchronize with the transmitter at the receiving end, and that's an important part of the process as well. Now, I mentioned already that we're talking about making minimal QSOs with very weak signals. We're going to try to optimize the ability of the decoder to dig down into the noise without making any errors in reproducing what was transmitted at the other end. And so, since we're interested primarily in one task, making minimal contacts, exchanging maybe a signal report and a grid locator and your call signs, and not much else, so we can structure the messages in such a way that we will require the minimum number of bits to do that. And a typical contact sequence that I show here, blue being one station that called CQ and red being the station that answered him or her, that's the basic scheme underlying the communication information in all of these weak signal modes. So it turns out that we can actually make the message packet as small as less than 100 bits. In fact, we ended up settling on 72 bits as the basic block of information. That is the same length as the header, the link connection header code that we heard about first thing this morning. This is the whole message, including the FEC and everything else. That's built into, sorry, it's not including the FEC. It's the user information block is 72 bits. We then expand that so that the actual number of bits that are sent over the channel are somewhat larger, maybe 2 or 3 or even 5 times larger, but it's still a fairly small number of bits. And we do that in the following way. It turns out you can encode any standard amateur call sign into 28 bits. They all have a number somewhere. And before that will be a prefix, which can be 2 characters, at least one of which has to be a letter. And then after the number, one of these might be a letter, like 5B4 instead of KA1. But anyway, then there's a suffix with up to 3 letters. And anyway, it turns out putting all this together means that you can encode the whole call sign, basically any standard call signs anywhere in the world, into 28 bits. Of course, there are funny special event call signs and things that have funny numbers in them, and we don't do that. Okay, that doesn't fit into the 28-bit recipe here. If you want to send a locator, a 4-character locator, 2 letters and 2 numbers that tell you where a station is on the Earth to within 60 miles or so in latitude and longitude, depending a little bit on what the latitude is. Anyway, that turns out that takes another 15 bits. And we actually added one, that would make 71. We actually added 1 extra bit. If that extra bit is set to non-zero, to be a 1, then the first 71 bits are all reassigned as arbitrary free text. So you can send anything as long as it only takes 13 characters as part of a message in any of these modes as well. So if you want to build up some message like that, that takes 71 bits, and then you have the 1 extra bit that flagged that packet as being a free text message. And you can count these up. 1, 2, 3, 4, because the space is also a character. 8, 9, 10, 11, 12, 13. Okay, that just fits. But longer things don't work. Okay, let me talk specifically about a few of the features of the current program, WSJ-TX. It's available with installation packages for all standard platforms, Windows, Linux, OS X. You can compile it for any Linux-like system. The source code is all available, and even some compiling scripts are available to make that fairly easy. It does implement rig control for almost all modern radios. Anything built since, I don't know, since the turn of the century, say, has some kind of cat control cable. The most recent ones even just have a nice USB connection. You connect that to the computer, and the computer can control frequency and band and various other things. All these modes do error-free communication for minimal QSOs, like I've already described. We do have really good decoders in here for all of these implemented modes. We get down very close to the famous Shannon limits, as close as are basically possible with the present state of the art. So that means that we're decoding things with signal-to-noise ratios on down to around into the -20s, depending on which mode we're talking about, where the signal and noise here that are being discussed are whatever the signal bandwidth is, and the noise bandwidth we've just taken to be fixed as 2.5 kilohertz, typically the bandwidth of a standard single sideband transceiver. So when we say the signal-to-noise ratio is less than 0 dB, it means that the signal is weaker than all that noise, but it doesn't mean that we're actually detecting things in a detection bandwidth at signal-to-noise ratios less than 1. We make the detection bandwidth as small as necessary to decode the signal that's being transmitted. And so, you know, we're not violating any physical principles here. The detection is actually done with software that gets down to bandwidths of only a few hertz, depending on what different mode is being involved. Among other things, we can actually do very accurate frequency calibrations of your radio. And there are macros for doing that built into the program. Basically, if you just use maybe a local big city standard broadcast station as a reference down at the very low end of the dial, and then use the various WW/V frequencies and maybe CHU, if you get those Canadian stations well, you can accurately map your radio's dial error over frequency. It always turns out to be a straight line with modern synthesized radios because it all depends on the accuracy of the master oscillator in the radio. So there's only one oscillator that is off a little bit. And once you calibrate that, you can get your radio to give you frequencies down that are accurate to the 1 hertz level. And that'll get you a gold star if you enter the ARRL frequency measuring contest, which is a lot of fun. It's a fun thing to do. Here, just in passing, are the signal-to-noise limits. Basically, the signal-to-noise ratio, again, defined with a 2.5 kilohertz reference bandwidth of these various different modes. Whisper is the most sensitive mode. It gets down into the minus 30 dB range, a little bit lower, and various others are shown here in between. Typical, a really good CW operator, like the guys that do moon bounce with CW, with the headphones on and concentrating and a lot of repetition and so forth, they can get down to signal-to-noise ratios around minus 15 dB on this scale. A signal that is weak but fairly easy to copy is more like 0 dB, and a single sideband signal, if you want to copy that, needs to be at least, say, 10 dB above the noise in 2.5 kilohertz bandwidth. Then you can probably make out what the guy's saying, but it's still a very weak signal. Anyway, these other modes all get well below that. So when you're making FT8 QSOs with stations around the world, and if you're getting signal reports for them in the negative 10 to negative 20 region, those are signals that you probably can't even hear. You'll hear a lot of tweedling if you turn up the audio in your radio while you're doing this, but that's mostly the strongest stations. If you're working the weaker ones, they probably, even if they were the only signal in the band, you wouldn't hear them very well, if at all. Okay, here's one fun slide just talking about the explosion of popularity of FT8 recently. The guy that runs the website associated with the Club Log group, where people upload their logs every now and then to the Club Log. And anyway, they mapped all the usage of different modes over calendar year 2017, last year. And FT8 was started around mid-year in July. So there was zero activity on FT8 before that time. And you can see the lines there for CW and phone and JT65, which is a popular mode, but is becoming much less popular because FT8 has sort of taken over from it. It's astonishing that at least near the end of the year, FT8 was making well over half of the calls that were being uploaded to Club Log. Pretty interesting. And was not what we were expecting when we released that capability in the program. Anyway, here's the program again. That was basically my title slide that you saw. So the upper colored vertical stripes, that's the waterfall that shows the signals. Those green horizontal lines are separated vertically by the fixed time period that is occupied by each FT8 transmission. All of these modes used timed sequences, so the transmission always takes exactly the same amount of time. For FT8, the transmit and receive sequences are 15 seconds long, 4 of them per minute. So those green lines are separated by 15 seconds. And in between those, you can see the various signals coming and going as people are working each other. Typically, again, the numbers across the top are frequencies in hertz. The receiver is tuned to 14074, the 20-meter frequency at which, by convention, people have been using this mode. You can use it anywhere, but that's where the group of typical users will be found. And the frequencies, so that's the dial frequency of your transceiver. You've got it set in upper sideband mode, and the frequencies across the top are then frequencies in hertz above that dial frequency. So you have basically a 2 kilohertz slice of spectrum there. I let the waterfall run up to a little over 3 kilohertz just to show that the concentration of all the signals are basically in one little subband, 2 kilohertz wide, or two and a little bit more. Because the decoded signals don't make mistakes in call signs, and because many of the decoded signals will include a 4-digit grid locator that tells where the station is, it's very easy to imagine how you could put all that information together at some central site, if it could be sent there, to produce a map of this guy working this guy and this station working somebody else over here. And that is done now routinely because WSJT sends all of its received decoded transmissions that include a locator to a central site called PSK Reporter. And you can bring that up on on your browser, and it basically shows you who's working who worldwide using the FT8 or any other mode. You can select the mode, you can select the band, you can select even a particular call sign. Maybe you only want to see who's decoding your own signals. Put your call sign in there and it'll tell you. That even if you haven't worked these people, if they are on and have their receiver running and they're connected to the internet, your connection will show up here on the map, and I'll show you some examples of this in a minute. The different colors correspond to different bands. Here I had selected all bands. As it happens, at the time this screenshot was made, which was just earlier this week, in the middle of the week, there were, what does it say, 2,638 FT8 monitors on. So worldwide, there were a lot of people listening. And if I put a signal on, I could quickly find out where I was being decoded. Let's just go through these a little bit, one band at a time. So here at a particular time were the people that were using FT8 on 160 meters last week. Obviously, 160 meters is a nighttime band. So over here, nighttime. Over here is daytime. A lot of Europeans on working each other. A few of them are working out into Japan or into Australia. That's good DX on 160 meters. Mostly we're talking about fairly, contacts within a continent anyway. Here's on 80 meters at the same time. Here's on 40 meters. 40 meters is a better DX band, so people are working a lot farther away. Even working across the Atlantic, even though it's daytime on our side at this point, we're still getting through this low part of the sunspot cycle. You can do that. Here's 30 meters, a lot more transatlantic stuff going on. Here's 20 meters. Now, of course, 20 meters is primarily a daytime band, so lots of that going on and lots of DX across the Atlantic. The Europeans have pretty much gone to bed at this point, and over here it's in the wee hours of the morning, so nobody's on. But you can sort of see what's still. And 20 meters doesn't close immediately at sunset. You get a few more hours after dark, typically. Here's 17 meters. More and more now we're getting into the frequency range of daytime bands. A lot of north-south stuff going on now, trans-equatorial propagation. Recently, the higher bands haven't been any good at all, but the day that I happened to do this, even 15 meters was wide open, particularly on north-south paths. Even 12 meters, and even 10 meters was wide open on north-south paths. So the Europeans and North Americans were all working to South America at this time. That was fun. So lots of people are on, lots of people are using FT8 and having a lot of fun with it. So let's carry on. One more slide here on, again, still looking at this website called PSK Reporter, which, by the way, has nothing explicitly to do with WSJTX, except that Phil Goldstone, the man who runs PSK Reporter and who wrote it, worked with us to make sure that the interface was proper and that we were sending him the information he needs to do it. Here I selected in the mode column over here at the upper right, selected, let's see, oh, we don't want that one. I guess I want that one. We selected MSK144 instead of FT8 for the mode. We selected 6 meters over here. Actually, I have all bands, but the only band on which people are using MSK144 routinely is 6 meters, so all these are red, which is the color for 6 meters. You will notice that apparently somebody is working into, what is that, Cyprus or Crete or something from the East Coast. Almost certainly that's spurious. I don't believe that. This guy, or some guy over here, is not using cat controls, so the program doesn't know which band he's on. And he switched bands after he last told the program which band he was on. So that's probably a 20-meter signal or something. And Phil Goldstone, the author of PSK Reporter, has worked up a scheme of identifying people that are misidentifying their bands, and you can check his list to see if that's believable or not. It almost certainly is not in this case. What in fact these people are doing, say within North America or within Europe, is they're working each other by meteor scatter. So those typical distances are what, 500 miles out to 1,000, 1,200 miles or so by meteor scatter. A few words about recent statistics of people using this mode FT8. I should mention, by the way, why are all these other modes JT something or other and this one is FT? Because originally it was just based on my call sign or my initials, but the co-author of this mode is Stephen Frank. That's where the F is. So it's Frank and Taylor FT8. That's I don't know, probably we should have had a better name, but that's what we came up with. Steve Frank is Kilo 9 Alpha November. He's a professor of electrical engineering at the University of Illinois, Champaign-Urbana. So another professor, if you like. Steve is not any more than I am an expert in this kind of coding and information theory, but he's in a department that has lots of people that do that. And so he actually has been sort of moving across subdisciplinary boundaries recently, talking to his colleagues and getting us a lot of good new ideas that we're putting into ham radio software. Typically, recently, the number of spots that are sent to PSK Reporter every hour is around 500,000. A bit more on a weekend and a bit less in the middle of the night in North America and Europe. But typically 500,000, I mean, typically 1 million per 2-hour slot, if you like. That's a lot of receptions. It's not too hard to see where they come from if there are more than 10,000 users and they're all receiving each other. But anyway, whenever they receive a message that has 2 call signs and a locator, that message is sent to a PSK Reporter, and that's where those maps come from. Typically, the number of active monitors on the air at any given time, over any hour, is a couple thousand, anywhere up to 4,000 or so. Again, there's a daily cycle, fewer when it's nighttime across the Atlantic, sort of, because the Europeans and the Americans have gone to bed. That's where the biggest activity is. But there's activity around the globe. The number of active transmitters in any hour may be a little higher, presumably because some people don't have their things configured to send their reception reports to a PSK Reporter. Interesting, among the various statistics that you can get from clicking on a little button on the bottom of the PSK Reporter screen is how many different DXCC entities have been decoded by a particular station over the last 24 hours. And typically the guy at the top of the list is well over 100, sometimes closer to 200. Certainly if you extend it over 7 days, which he also does, the top number of reception reports is a couple hundred DXCCs. It's very clear that if you care about it and would like to work 100 different countries with FT8, you can do it in a week with no trouble at all. And this, you don't need a kilowatt and a beam. You need 100 watts and a good dipole because the signals don't have to be strong. They can be well below what you would need for sideband or even CW. Okay, let me say a few things now about Whisper, the other of the most popular modes. Again, I'm emphasizing here things that are sort of have the widest interest and the largest number of users, even though the motivating philosophies underlying the development of all of these different modes typically were based on things that happen at 50 megahertz on up, because those were my particular interests at the time. Anyway, so the weak signal propagation reporter mode, pronounced Whisper. It's a low power, one-way mode. You don't make two-way contacts. That means we don't really even need 72 bits in the basic frame because we're only going to send one call sign, a locator, to tell where that station is. And we added one additional field, which is a number characterizing the transmitter power in dBm, decibels above 1 milliwatt. So 30 dBm is 1 watt. 37 dBm is 5 watts. When I run Whisper, I typically run 5 watts. So that's the message that I configure my Whisper setup to send. But anybody else would have a call sign, their locator, and their transmitter power. Some people have been doing this with transmitter powers of 0, 1 milliwatt, and they still get reports from around the world when conditions are right. Whisper, like the other modes here, is a very low bandwidth mode. It uses 4-tone frequency shift keying. So it's basically at any given instant, it's transmitting one of 4 different frequencies. They're separated by about 1.5 hertz, so the total bandwidth is 6 hertz. Again, you configure your software optionally to send your reception reports to a central database. In this case, it's called whispernet.org. And again, this allows the WhisperNet guys to have written software which shows signals starting at transmitter A and being received at receiver B, and you can plot that up on a world map. Typically, there are something like 1,500 Whisper stations participating on an average day. It's a little higher on the weekends and so forth, but people typically run their receivers all the time. In this country, we're not supposed to run unattended transmitters unless you're a beacon assigned and working in a beacon mode. So you're not really supposed to run Whisper with your transmitter transmitting on some of the time unless you're in control. Some people claim I'm in control even when I'm sleeping because I'm only right, nearby, whatever. I don't think we would say that in writing with the FCC present, but anyway, I think that's what some people do. There are almost 1 billion spots that have been sent to WhisperNet since 2008. Remarkable. But it's been popular. There's what the Whisper program itself looks like. Actually, it isn't. There is a separate standalone program called Whisper, which many people have used for many years, but currently Whisper is also built into WSJTX. So if you just switch modes in WSJTX, you get into Whisper, and it's basically the same. So again, you see the waterfall at the top, different signals. The Whisper transmissions, instead of being 15 seconds like for FT8 or 1 minute for almost all the other WSJTX modes, Whisper transmissions are 2 minutes long. And you configure your setup so that you transmit a certain percentage of the time and receive all the rest of the time. So a typical setup would say choose transmitting for 25% of the time or 20% of the time and receiving the rest of the time. That means in a given 10 minutes, you might transmit for 1 2-minute segment and listen for 4 2-minute segments to make up the total 10 minutes. It'll be something like that typically. And basically the receiver, the decoder simply displays who it is you've decoded, where they are, how far away that is. This is distance in kilometers, I think. And again, what their transmitter power was. You can see most people are running transmitter power around a watt, 30, 30, 30, 37, that's 5 watts. Here's a 23, so what's that, 20 milliwatts? It's pretty low. 200 milliwatts, I guess I'll make that. Anyway, you can see what the various ranges are. So here's the WhisperNet map. I have there, I think, selected all bands, so you're seeing worldwide activity, people whispering to each other. Each little location has a call sign associated with it that's flagged. You can, again, you can instruct the map to plot only those dealing with a particular call sign or call signs, only from on particular bands, so forth and so on. And I guess I have a few more of those maps coming up. Here's a plot of the number of Whisper stations that are actively participating, going back to the time when the mode was first released in early 2008, just about 10 years ago now. And so we started from no usage at all, and currently we're up to around, what is it, 1,500 active users. The blue curve is the number of different calls heard, and the red curve is the number of actual stations sending reports to WhisperNet. So again, there's some people doing things here without sending in the reports. That's fine. You don't have to do that. Here's the number of Whisper spots per day, which has also been ballooning recently. More people are finding out about it, deciding it's fun, building little systems that run only a few watts or a few milliwatts, maybe running it on a Raspberry Pi, which is easy to do, and that's a lot of fun. The different colors here represent different bands. So the light blue, for example, is 40 meters, a good DX band. The darker blue is 30 meters, also not a bad band. The green near the top is 20 meters. Okay, here's a few more WhisperNet maps. Here's what you get when you put in a particular call sign. I put in my own there, so it's centered on central New Jersey, and you can see the stations that were copying me or I was copying them, connected by lines. If I clicked, zeroed in and clicked directly on K1JT, which is in here under a couple of others, if I click on that, it'll pop up a little balloon that'll have in it all the call signs of the stations that are receiving me and all the ones that I am receiving. That's often of interest to a user. Let me talk about a couple of very specific Whisper-oriented games that people have played recently. A guy up in Toronto, VE3KCL, has made a solar-powered Whisper system, which he flies in balloons. Here are a couple of party balloons, foil-type party balloons. He's used transmitters made by QRP Labs, Inc. You can order the boards. They're only $30 or something. The whole payload held up by these 2 party balloons weighs about 2 ounces, a little less than 2 ounces, 39 grams. So below the balloon is a quarter wavelength at 30 meters. So what's that? 7.5 meters of aluminum wire. Then there's the transmitter and other electronics. And then there's another quarter wavelength. This is the half-wave dipole, half-wave vertical dipole with a transmitter in the middle and a GPS receiver. And boy, is this fun. So they launched this thing and it went around the world. Okay, it took off here in Toronto. It did this across the Atlantic and then all the way across Southern Europe across Northern Africa and Southern Asia. And then across North Korea probably, I don't know. Then across the Pacific, and here it is back past, they had a huge celebration when it went past the longitude of Toronto because it made a full 360 at that point. But it didn't come down yet, and in fact, it kept going. and finally went down in this Atlantic somewhere, a little bit north of the equator, but just shy of Africa on the second time around. Interesting. No, they didn't get it back. This was, I think, his balloon flight number 18 or something. He's done this quite a number of times. This was the first one that made it around the world. There was a second one as well. Interestingly, the red parts of the curve are actual tracking reports. Other people that just had their whisper systems running would send in that they'd received it, and they know where it is because the GPS receiver is currently updating the grid locator being sent out. The blue parts of the curve are nighttime, and this, of course, is solar powered. So when the sun goes down, the transmitter goes off the air pretty soon. The batteries only last a very short time. They couldn't carry very much in the way of battery backup in 2 ounces, right? So it's off the air here, but they do know the direction of the winds aloft. And so they can pretty much predict what it should do for the next few hours, and then they pick it up again. So basically, the blue lines are just connecting the dots, but with a little bit of extra information because they know the direction of the high. They also know the altitude. This thing is sending ordinary whisper signals on some of its transmissions, and specially encoded JT9 signals on other parts of its transmissions. So they actually have two bands on which you can receive them. And when that information is put together, they get not only the location in latitude and longitude, but they get the altitude, they get the battery voltage, and a few other bits of important information. Temperature, I think they get, maybe speed, something like that. Google VE3 KCL balloon, and it'll all come up, and you can look at the more details. Here's another, yeah.
What typical altitude is that thing going at?
Around 10,000 meters. So it's the same height you fly at, but do keep in mind that a 777 hitting this thing wouldn't even know it had hit anything. There's basically no mass there. I don't think it's an aviation hazard. Here's another fun game played by a friend of mine, ZL1RS, who built an ocean floater with Whisper aboard. So here's his ocean floater. It's not tiny, and it certainly weighs more than a couple of grams. It's got a whip on it. It also runs in the 30-meter band. It has a transmitter about 200 milliwatts and a GPS receiver, and it's powered entirely by 18 D cells. So perfectly ordinary alkaline batteries are down here in the bottom part of this thing. It floats more or less upright, but of course it's being tossed around by ocean waves. Anyway, he got his friend who owns a sailboat to launch this, to take it from the North Island of New Zealand up toward Fiji. There's Fiji up near the top, and just let it go. So he dropped it in, and for the next year, this is what it did. Just following winds and waves and whatever. It ended up over here at just about the predicted time when the batteries should have failed. They did. It lasted, I think, 13 months. And it almost got itself back to Australia, but not at the same latitude. It had moved north quite a bit. Anyway, again, it was a lot of fun, and it had many people. Again, I received it myself on 30 meters many times in New Jersey. People around the world send in reports to WhisperNet, and WhisperNet, by the way, has a really good archiving system, so that if you want to know in the past who was receiving such and such a call over such and such a range of dates, you can get it from WhisperNet. You can download they basically just have a big disk file that keeps getting bigger and bigger.
Did they recover it?
I don't know. I don't think they did. I think it would be pretty hard. They knew what grid locator it was in, but you know, that's 100 miles wide and 60 miles high. You're not going to find it very easily. Okay. Anyone else? Well, I've pretty much covered what I wanted to cover, I think. What is WSJTX good for? Well, it's a lot of fun for doing a lot of very different things. QRP DXing on the HF bands is its biggest following currently, and that's why there are 15,000 or more users. But and those people have lots of different interests. Certainly certificate hunting, the recent ARRL International Grid Chase, I think that idea came up at the League after FT8 was released, when they saw it was getting popular, because every FT8 contact exchanges a grid locator, so you might as well have some certificate associated with it, I guess. It wasn't my idea, but anyway, that's what they came up with. It's used a lot now for VHF contesting, where you can work a lot of extra grid multipliers by using the digital modes that get down into the noise. That's particularly important, more important than it might have been 20 or 30 years ago, because a lot of hams today don't do Morse. Period. Never learned it. But it's still good, really good, for meteor scatter and moon bounce, which are the things that it was originally designed for. But so you can see hams are very inventive. They have put our software tools to use doing a wide range of things that either we didn't imagine, or maybe we imagined they might be of interest to some people, but didn't think would be the driving forces behind any of this stuff. But it does work very well for meteor scatter and moon bounce, and I'll just say a word or two about that. There's my own moon bounce antenna on 2 meters. On 2 meters, 140, I've got 4 Yagis, they're each 14 elements. And you can see that the EME antenna there is raised, pointing up at the moon. The other antennas on the same mast don't elevate, they just rotate. So they're looking horizontally while the EME antenna is pointed upwards. But I have worked all states on 2 meters. I've got 134 DXCCs, I think, the last time I checked. So this does really work, and there are a lot of people that use it around the world. All those QSOs, essentially, almost all of them. I may have made a few hundred on CW, but most of them, thousands of QSOs, were made off the moon, reflecting, with JT65 as the digital mode. Interestingly, one of the most recently implemented modes in all of ours is this one called QRA64, Q-Array repeat accumulate mode with 64 different tones. It's been used a lot recently for moon bounce on the 10 gigahertz band and even the 24 gigahertz band, where you can actually do moon bounce with a little dish about this big. My friend Rex Monker, VK7MO, likes to drive around in the Australian outback, going to different grid locators and giving his 10 gigahertz friends a contact off the moon to build up their grid locator total. They have a great amount of fun doing this. Rex is retired and he loves driving around in the outback. Let's see, that little system there, he's got I think it's a 2-foot dish, 70 centimeter dish on a tripod. I think it's just an ordinary camera tripod. He's running 50 watts at the feed. I don't think he can work another station the same size. The guys that he worked typically have a 2-meter dish, 6 feet or so across. Not a lot bigger, but somewhat bigger. We've been trying to get to a point where we can actually have 2 dishes that you could put in the back of your station wagon, have them work each other off the moon. We're not quite there. I think we're only shy by 3 dB or something, but we need a little bit more power. Currently, getting 100 watts on 10 gigahertz is not that easy, particularly not if you want it to be portable. You can buy surplus TWTs that will get that much power, but those have complicated power supplies and they weigh a ton, and you don't want to put that in your car. So just a few final words. We do have a home page. If you Google WSJT, that's where you'll get. I suspect there are more than a few people in here who are good with software. If you're interested, all this is open source stuff. The user interface in WSJTX is written in C++ using the Qt or Qt framework, but the heavy-duty number crunching is actually done in Fortran because that's what I do well. but we also use Fortran. Don't laugh. Fortran is an ancient but honorable language. And it's whatever. We also, C or whatever we need, we use. The version control is done with Subversion. Maybe many people here probably know that. We have many contributors to the software now. A handful of ones who have done a lot of the programming in the current program, and even larger, many handfuls of ones who have made some contribution, and more such contributions are always welcome. So I think that's a good place for me to stop. Thank you all very much for your attention.
Any questions?
Yeah, why the numbers? I think maybe in all those cases, I should have said this, the number refers to the number of different tones used in the frequency shift keying. In all these cases, we are generating a constant envelope signal. That is, we change the frequency of the signal, and that means modulating the phase in some way, but we don't do any phase reversals or phase jumps. So the phase is continuous, and that means that we don't even need linear amplifiers, which is handy for a number of reasons. It means the signal doesn't widen out the way a PSK31 signal does if you overdrive the transmitter. These signals are basically all constant amplitude, so they don't do that. JT65 uses 64 tones for data and 1 tone for synchronization. That's where the funny number 65 comes from.
Dr. Taylor, I have a question from the chat room, from the live stream.
Okay.
Arnie would like to know, is EME possible on 2 meters with 100 watts and a reasonable size beam?
Is aiming. Oh,
EME.
EME.
Sorry,
yeah,
EME.
Yeah,
My apologies.
Yeah, definitely. 100 watts and a 8-element, 9-element, 10-element Yagi is sufficient to work some of the bigger stations on 2-meter EME. No trouble at all. 2 of those stations can probably work each other some of the time when the moon is in a colder part of the sky, but not necessarily any day of the year. There is a handful, maybe I know of 3, I think there's probably more like 6 or 8 now, single Yagi stations who have worked DXCC on 2 meters. So there are enough big stations around that you can work a lot of them.
Thank you.
Yeah.
For EME, is it better to use UHF, 440, or 2 meters?
Yeah, 2 meters because there's a lot more activity, but 440 or 432 actually because the sky is colder and therefore you can do it with less power. So you make your choice. 432 is a great band for EME, although it's not as good as it used to be because of the number of oscillators and everything that we buy these days is filling up the band with birdies. That's also happening on 2 meters. But 2 meters has a huge amount of EME activity, and so I think it's the best band to start on.
Could you say just a word about the de-expedition mode, please?
Oh, yeah. Okay, so people who are already using FT8 know that there is coming a mode that we have called FT8 de-expedition mode. We made it basically at the request of the de-expedition that's going to Baker Island in June or July, which is one of the top 10 wanted DXCCs, and they're expecting to make many tens of thousands of QSOs. Ordinarily, they're primarily like DXpeditions are. They're going to be primarily sideband and CW, but they are going to have, they would have had a RTTY station as well. But they've decided, forget RTTY, we're going to do FT8. Cool. But we'd like it if FT8 could make QSOs faster than once every 2 minutes. 2 per minute, which is basically what you can do with standard FT8. So we scratched our heads for a while and decided, well, maybe we could make it go faster. We wanted to stay with the 15-second transmissions, but what else could we do? Well, among other things, we could make the DXCC, make the DX operator work more than 1 station at a time. So that's what we're doing. We're basically allowing them to add together up to 5 standard FT8 signals, separate them by 60 hertz on the band, so they'll be right after one another. So one of these signals may be calling CQ while another one is working somebody and another one is saying 73 to somebody. They're finished with it. Anyway, that's the basic operation. And we have showed more or less that it, in the lab, that it works up to something like 500 QSOs per hour. Well, that's a pretty good rate. I doubt that'll be achieved on the air in a pile-up with a lot of QRM and whatever, but we have built into it some schemes that we hope will minimize that. For example, the DX station will stay in the low end of the 0 to 4 kilohertz audio band. He'll stay right where he is, pretty much. If there's deliberate QRM, we have a way of evading that, but otherwise he's going to stay put. Everybody else has to call from 1,000 to 4,000 hertz. Okay, they don't go in the low end of the band. They stay up above 1,000. As soon as the DX operator decodes somebody and calls them, that station is going to then jump down below 1,000 hertz to send his final report. He's going to, okay, you called me, here's your report, and I'm in a clear part of the band now. And the DX station then says, thanks, got you, 73, you're in the log, and then he works somebody else. So basically, all of that is handled by the software, the automatic QSY into the low part of the band. Well, we've tested this on the air a number of times with a private group of a few dozen people, and it pretty much works, but we still got bugs in the program. We tested it once with a public request for other help, and that worked also, sort of, but it had bugs. So we're going to have another public test run coming up, and I hope within one or two more test runs, we'll get the rest of the bugs out of it and have it working. How it will actually work in a dog-eat-dog DXpedition pile-up, we'll find out, I guess. It'll be fun.
So as a follow-on to that question, one of the issues that I've noticed with FT8 is that people don't necessarily pay attention to what they're transmitting on top of. And are there plans to build some kind of avoidance into the upcoming versions?
So far, we've pretty much left that to the same kind of techniques we always use, and that is if you're not getting through, you move a little bit up or down and hope that you will. We've been very careful not to let the program make robotic contacts. It would be pretty easy to do that. We didn't want to. So you can't turn your thing on and let it run overnight and come back in the morning and find out who you worked. It doesn't do that. It doesn't do that by design. But as far as evading QRM, the only thing we've got in there that helps in that respect is that, and actually this is an important point for any of you who do any DSP kinds of stuff. Once a signal has been decoded, because it's a fixed 72-bit user message, if we've decoded it, we are 100% sure that it's right, and therefore we could re-encode it so we would have a waveform exactly equal to the waveform that was transmitted. Aside from maybe a little bit of frequency shift because the oscillators aren't exactly the same and a few other details like that, which we can basically peek up on in the software. We know exactly what was transmitted. So we can subtract that transmitted signal from the total that might have had 50 signals in it. And if there was another signal at the same frequency underneath the one that we decoded, then we can decode that one too. And if you look at what comes out of the stream of decoded signals, you will see they're in frequency order because we just sort of stepped through the total received passband in order. But it'll get up to 2,500 hertz or so, and then you'll see 3 or 4 extras at lower frequencies. Those are ones that were decoded on the second pass after the first, presumably stronger signal was already subtracted. We pioneered that with JT65 when that was the most popular mode. It worked very well there, and then so we've done it also in FT8. It's also done in Whisper now. So the decoders make multiple passes, subtracting out each decoded signal after it's decoded.
Is there been any effort to adapt this for use in Pactor type situations, such as like a better version of HF communication?
The simple answer is no. It certainly could be done. I don't know that it would be a huge step forward, but I mean the principal difference, I guess, with respect to a general purpose data transfer mode like Pactor is that we have built-in forward error correction, not just error detection. So yes, that definitely could be done. And you probably could design a better system in some sense than Pactor. But we've also noticed that coming up with a better mode doesn't necessarily mean people will use it right away. It has to be a lot better. There's a lot of inertia in the system, and people already have something running.
It's very expensive, and if we were getting modems that would be people with software instead of having to pay
Yeah.
$2,000 for a modem.
Yeah, well, you just heard about one way of doing that, obviously, with Direwolf. Yeah, right.
One more.
Good.
Our club is trying to track a gentleman that's coming back from NZ land sometime in April, and your call sign there from New Zealand caught my eye. If somebody wanted to put a bird on the boat, we might be able to arrange a mutual contact. He's down there tramping around right now, so it might be something to keep in mind. Also, there's one spot open if somebody wanted to sign on his crew.
Oh, okay.
The boat's about 30 feet long.
Sounds like fun.
All right.
Signed me up about 30 years ago, but I'm not.
Thank you very much.
One question on gravity, please.
Oh, yeah, okay.
Down in Hanford, in southeast part of the state, a Nobel Prize was awarded last year. Could you speak to that and compare it maybe to yours?
I think that's one of the most important advances in physics in the last 100 years, and I'm proud of the fact that it was in an area that I contributed a lot to earlier. Interestingly, the work that I did in from late 1970s or early 1970s, actually, up until the honor from the Swedes in 1993, basically established that the gravitational radiation that was detected by the LIGO detector in Hanford and its twin over in Livingston, Louisiana, we basically established unequivocally that that kind of radiation does actually exist, because we could measure the rate at which energy was being lost from an orbiting star system, a pair of pulsars orbiting around each other, losing energy in the form of gravitational waves, and the energy loss rate is what we could measure so accurately, and that was precisely in agreement with Einstein's relativity theory. So the questions about, but whether this gravitational radiation that Einstein effectively predicted but thought would never be detected, does that truly exist? Because, until we've done an experiment, well, all we can say is this theory is consistent with that radiation existing, but in the end, experiment has to answer the question whether it's true or not. Anyway, we showed that it is true, and that was part of the reason that LIGO, a big science project that required $500 million to get it going, was plausibly going to be successful. I think without the experiments that I did, it probably would not have been fundable by Congress or by the National Science Board. So, very exciting.
Thank you very much.
Thank you. Thanks.
Get you loose there.
Gotcha. Okay.
Thank you. So we have a break right now. We have some little brownie things and chocolate, cookies, and some other things out on the tables. Help yourself. And no, they came from Costco, right? Yes.
That's at the 420.
All right, let's go ahead and get started again. All right. Get till 4. Does that work for you? Yeah. Okay. All right, so our next speaker is Brian Hoyer, who many of you know, have seen in the past. Brian Hoyer, K7UDR, is an inventor and entrepreneur with over 30 years' experience in Silicon Valley. Brian founded Northwest Digital Radio in 2012 to advance digital communications via amateur radio. Thank you for joining us, Brian.
Thank you, Scott. Okay, first off, I want to say that I talk at a lot of these things, and this conference has some of the best speakers and some of the best attendees of any conference I speak at. So give yourselves a hand. And then let's talk about all of our speakers up to now. What a schedule, what a fantastic thing. How about another hand for them? You know, Hoos came out from the Netherlands to talk here. That's how popular you guys are. Now let's move over to my main slide. So this, to the ladies in the room, this is not what you think it is. It says right across the top, this is the Art Nouveau period, which is circa 1890 to 1910. And that's important because in 1888, Heinrich Hertz proves that electromagnetic waves exist. I had radio waves originally, but I read some further and found out that the term radio didn't come into use until later. In the 1890s, of course, Marconi did his wireless telegraphy. Amateur radio is born in the early 1900s. Doesn't have an exact date. I think 1904 was when hams first got access to wireless telegraphy equipment. World War I ended amateur radio. It's actually killed. It also ends the Art Nouveau period. This particular picture I was given 2 weeks ago for my 60th birthday. It was done by my daughter, Brittany, because she knows I like the Art Nouveau period, and she incorporated our logo into it and put in the amateur back in amateur radio. So, thank you all. All right, we're going to talk a lot about APRS. We're going to talk a lot about the amateur radio community because that's what's in this room right now. It's not just about radios and equipment and technology, that's all important. It's about the community. So we're having a lot of conversation about the Raspberry Pi, so I'm just going to reflect back a little bit on where the Pi came from my perspective. Back in 2009, one of our club members walked into the club with a $100 box called a Shiva plug. And it plugs right in the wall, AC, has an Ethernet port, and it was a Linux server. And I thought, wow, that is really cool. And so that just got me thinking that that would be a good thing to do to incorporate into a radio, but the form factor was wrong, the power supply was wrong, it was just the wrong thing. So they're down in LA. This is based on the Marvell chipset. So I contacted them and said, okay, they're 99 bucks. If I get rid of the case and the power supply and the cable and the packaging, and I buy 1,000 of them, what do they cost? And they said, $99. And I said, okay, you're going to lose this marketplace. So I built one. This is in 2011. We built this computer which has, well, look, it's got Ethernet and 4 ports of USB. It's got an micro SD card over here, 40-pin header, 5-pound power supply. I got these built in China for 50 bucks a piece. And they sold them into, get this, the education market in China, and they were selling 10,000 a month. So that was a pretty decent thing to do. But then, this happened. That's actually a Raspberry Pi 2. If they'd have seen my board, they would have gone to the 2 earlier. Now, this is based on the Broadcom chip. The original Pi only had a 26-pin header. They figured out there weren't enough pins. They didn't have enough USB ports, but they got there eventually. And so, doing the right thing to do is we switched over and said, well, if I could build 1,000 for $50 or buy one for 35, let's just buy the one for 35. But there's a more important piece of that decision. The decision is based on the number of developers on the Pi. When we had our card, we had several developers. I think they're all in this room. But the Pi had thousands and then tens of thousands of people working on it. So it's a great thing. Here's just a quick comparison of the two boards. Functionally, they're a lot the same. Area-wise, they're a little different. But there's the winner. And so to turn into a radio, you had to add the things you need to have to make a radio interface out of it. So what we basically built is a thing that's been shipping for a couple of years now called the UDRC2, which is a Universal Digital Radio Controller. And what's on there is, well, there's a bunch of stuff. It basically provides 2 4-wire interfaces to radios. It's Pi hat compliant, meaning it's got a little bit of EEPROM on there, which tells the Pi when it boots what's hanging on its head. So it loads the appropriate drivers. So that gets the configuration right. It's got a 12-volt buck converter. That's important for a couple of reasons. One, I don't have any 5-volt radios. I got 12-volt radios, I got 12-volt batteries, we got 12-volt stuff. Also, the little bricks you buy to power the Pi over the cheesy micro USB connector, the Pi needs a decent amount of power, and by putting the regulator on the hat, you get 5.1 volts at the pin, not 5 volt, 1 volts 6 feet away through cords that are powering 3 other things. It's a full 3 amp power supply. Also has a sound card interface, which is what you need to talk to the radio audio. It doesn't have all the stuff you'll find in a signal link because all of that stuff makes it perform poorly, okay? Transformers and things, those are things that some people back in the day with PCs needed to deal with noise inside the processor, but they're no longer relevant today. We want that direct path into the radio. So it's a high sample rate sound system, and there's PTT via GPIO, standard open collector stuff, which gives us radio control. So I named this the APRS of things, which wasn't my original thought. And of course, it's a direct knockoff on the IoT, the Internet of Things. You know, little devices all over the place that can do this or that. But why do that over amateur radio? Why just can't we do everything with Wi-Fi? And there's a number of cases where I think that you may want to look at something else. First off, you could be in a rural location without internet. Does that still exist? Well, Joe just talked about the Australian outback. Not a lot of internet there. 2/3 of the world is covered by water. And there's no internet in the ocean. Interfish? Interfish. Is that where one fish talks to another? It's like a chain thing? It's a relay. A lot of delay. And then the last reason, you know, what about when the internet goes down? So some of us are involved in MCOM. Some of the things you want to do, it's information that we might even be on Wi-Fi normally. But when things go down, we want to have another means of communication. And lastly, come on, it's amateur radio. We like to do stuff that's just may not make any sense whatsoever, but it's fun. So here's my first example of an APRS thing. Now, a friend of mine's got a cabin. This is San Juan Island. How many folks are from Washington State and know where the San Juan Islands are? Okay, so for those of you who don't know, There's islands in Washington. There's actually a bunch of them. A bunch of them are up here, and in fact, this island here, San Juan, I live right in that little blip right there. Victoria is down here. So I'm north of Victoria, Canada. Here's the border. In fact, from here, I can see Canada from my house. So my friend Bob has this cabin over on Stewart. Stewart doesn't have power, and Stewart doesn't have fast internet. And so Bob's got this problem. He has a generator, Stewart Island. It's off the grid, it's got slow internet. His generator's on a timer, an old dial-up timer, and it runs for 2 hours twice a week. And that charges batteries and pumps water and keeps all of his system going. It's bad if a generator doesn't run. But last November, he found out what's worse. What if it doesn't shut off? Well, it pumped the water tanks full, and then it kept pumping. But at least the person who cleaned it had left the shower on, so it didn't flood the entire cabin, but it flooded most of it. So happens I was working with Bob on another project. We were doing some monitoring using SDR dongles for aircraft frequencies. And I had this delivered to Bob, and I was telling him about this kind of stuff. And he said, well, I want one of those. So I said, sure, we'll build something. So we put together a Raspberry Pi and a UDRC, and we needed a radio. And my original concept was, well, Bob's here and I'm here. I'll put a transmitter here and a receiver at my place to monitor that so I can shove it into the internet and make this work. So I built some software, a little Pi stuff. I'm not a programmer, but I do play one on TV. And I put it all together. Thank you. And I put it all together and actually built a little monitoring thing at my place to check it. Because what I wanted to do was, first off, I want to beacon occasionally. And as we said earlier, not the one that says, my house is still here, my mouse is still here. You should say that occasionally, but not too much. But we do want to know that our station's still alive. So it beacons and says, Stewart Island is still here. It also, when the generator turns on, it sends an APRS packet that says the generator turned on. And you can go to APRS-FI and find it. And then when the generator turns off, it sends a packet that says the generator turned off, and it ran for 2 minutes. And here's where the monitoring came in, 2 hours. We were originally going to monitor it so we could shove it into like an email or something, but I found out there are amateur radio people who run a direct APRS to email server, which works off of APRS-IS, which is the internet side. So that problem was solved. I found another one that runs a server from APRS messaging to an SMS gateway. So over Christmas, I had Bob in the room. I put this together, and I showed him that, we turned the generator on. I faked it with a battery and a plug, and it sent him an email. And we turned it off, and his phone went off. And look, it was amazing. We only have that because of the amateur radio community. The fact that people are willing to do that, and these servers aren't free. They have to be, they're charged per message to send them, but they're willing to do that. So I made a donation to them, we got that running. So this is one of the first examples of the APRS of things. Let's see, this is Bob, K7NHE. Oh, another cute part of the story. So Bob used to own ICOM America. So Bob's got radio cred. And I said to Bob, he says, well, what do I need to bring? I said, I just need, any old 2-meter rig with a 6-pin mini DIN on the back. He said, okay, I'll get one. So what arrives is a $2,000 P25 radio. And I said, Bob, that's a little overkill. And he goes, well, not really. The FCC changed the rules, and we lost our type rating, so there's a big stack of them in a warehouse someplace, and they're free. All right. Stewart Island, grid monitoring. Catherine Creek. So not far from here, just east of Lake Stevens, is Catherine Creek, which runs into Snohomish Creek, which runs into the Snohomish River, which floods from time to time. This happens to be KK4 SOA. Brett, that's my son. He bought a house in Lake Stevens when he moved out here, and he asked me to come over and look at it. I said, sure. So we're walking the property with the real estate agent, and I said, what about the flood insurance? And the real estate agent said, well, you don't need flood insurance because you're not in a floodplain. I said, I'm pretty sure that's a creek at the back fence. Well, yeah, but it's not a problem. Well, $2,000 later, when they got the flood insurance, that was taken care of. So here we're doing something different. We're putting in a creek level monitor. It uses the 1 watt spot, which is something that we introduced at Dayton last year, but didn't take into production because we weren't happy with the RF performance. I'll talk more about that later. But instead of being an interface to a radio, we put the radio on board. And in fact, there's one of these at Basil's house on Lopez that's been up for the last year, just spitting packets out into the universe, partly so we can look at the propagation characteristics both directions. So that's another product we're working on. In an urban area, 1 watt is plenty. He'll also take this to Wi-Fi over to his house, and then the internet will be at his backup. The other neat thing about having the transceiver on the board is it now becomes a frequency agile radio. And that's got some benefits. Back in 2012 at DCC in Atlanta, I did a presentation called Control Channel, a hailing frequency for packet radio. And when I put this presentation together, I was nervous about it because I wanted to use APRS for this function. And I thought, boy, I don't want to run afoul of Bob Berninga. Because for anybody who knows Bob or has heard from Bob talk, Bob, the inventor of APRS, is a wonderful human being, but he has a pretty tight rein on all things that happen in his space. So I described this problem of the challenge of what channel should we park our radio on? And I'm always of two minds on this. First, I want to be on the channel that everybody else is on, because that gets me to the most people. Until I want to have some data, then I want to be on a channel that nobody else is on, so I got a clear channel. And so I created this hailing frequency for packet radio. And I put this dilemma out to the crowd, Bob sitting in the back, and I said, and what frequency should we use? And this guy in the back yells, 14439. I said, thank you, sir, your name? He goes, I'm Bob. Like, okay. And Bob blessed it, but if you think about this, there's nothing new here. Because trunk radio works that way. There's a control channel, a pool of frequencies. You hand them out on a case-by-case basis. Marine VHF works this way. If you want to get a radio check on Marine VHF, what do? You go to channel 16 and say radio check, and immediately some boater will say, you're not supposed to do radio checks on channel 16. And you go, thank you very much. You're supposed to do them on 9. Right, nobody monitors 9. In fact, I keep a boat name to keep myself legal. I have a boat called Aqua Firma, just in case anyone's listening. And of course, HF nets work this way. You go through an HF net and they're going, Puyallup, they're making all the calls, and then someone says, I have traffic for so-and-so, and the net control station says, go down 5, and handle your traffic. I'm looking at Joe Taylor. I'm thinking a lot about the fact that how do you get a frequency agile radio? Well, one way is you get the 1 watt spot because it is frequency agile from channels. Another way is use rig control. In a 706, which is a VHF, UHF, or an 817, we could QSY with that. But if you're doing any one of the modes where you have a bunch of channels packed into one band, you can QSY without dinking the radio. So that's important. Here's another one. I have a plane. I used to say it was a little Cessna 150, and then I realized that all Cessna 150s are the same size. But it is a little plane. And when your plane sits in your hangar, you have this issue of, in the winter when it's cold, you'd like to turn the preheater on, but you would prefer not that anybody else turns the preheater on in your airplane. Now, this is one of those cases where my hangar has internet available, but I don't want to buy another internet program for 50, 60 bucks for a function I'm going to use 6 times a year. Well, back in 2012 at MicroHAMS, I put forward this problem of when we're moving from telemetry to telecommand, we're taking action, we're dealing with men and material, as they would say in the military. We suddenly care more about who controls it. So this technology is called DTMK, which stands for Don't Touch My Knob. And it works very simply. This is another thing I talked to Bastille about, and I said, I think we need authenticated messaging. And he said, oh, I'm sure someone's done that. So I emailed Bob Berninga and said, is anyone doing authenticated messaging? And he said, no, but if you do it, please document it so we all do it the same way. So I put together a paper and presented the idea, and 2 years later, I was in Dayton at the APRS forum, and Andrew Pavlin got up and said, I got this problem. My in-laws gave me an RV, and it's parked at a remote lot, and I want to run the generator, but I don't want anybody else to run the generator. He said, so I found this paper from MicroHAMS, and if I could find Brian Hoyer, I'd ask him if it's okay if I could implement this. And I said, well, I'm sitting right here, so that's why we published it in the first place. So Andrew implemented it in YAC, which stands for Yet Another APRS Client, written in Java, so it's cross-platform. And he has authenticated messaging working in there, works with public or private keys. And I think that's a really powerful thing. It does require a time base where the transmitter and receiver are coordinated within 1 minute. That's to get rid of the replay attack. So if you memorize my message off the air, if you send it a minute later, it will be rejected. This issue is coming up more and more, the issue of knowing what time it is. Okay? There's some powerful things you can do if you have a very precise notion of what time it is. And then there's TweetGate. I was trying to figure out what to call this. This is not a political commentary, although it looks like one, which is why I like it. So APRS stands for Automated Packet Reporting System, not Position Reporting System, even though the APRS spec, not written by Bob, says Position Reporting System. And the reason I know this is because Bob invented APRS before consumer GPS existed. And he did use it for position, but it was more like tactical position. We're working a race, this guy's at start, this guy's at finish, this guy's at milepost 43. Those were the kind of positions they used. The first commercial GPSs came out almost 10 years later. Magellan made the first one you could buy. It was $3,000, size of a shoebox. I gave this talk at a club meeting and I said, who owned one? And one guy said, I had one. I said, really, you spent $3,000 for a GPS? And he goes, yeah, I just wanted to play with it. Like, okay. So we know that. And then APRS, I used to say it's the original SMS, but I'm wrong, because SMS, short message service, is one-to-one. APRS is one-to-many. So it really is the original Twitter. It's a one-to-many format. So it's highly useful. And another friend of mine, he was in Mumbai when they had that big hotel blow up. And he picked up his cell phone and he banged out to his mother in California, "Mom, I'm okay. Send." I think he got the last message out of Mumbai. If not, it was close to. He says it went down not long after that. And I'm thinking of the value of a small message, a small concise message that you can get a large distance. And we know we can have digipeaters and that gets it local and that's good. And we can have iGates and that shoves it into the internet if it exists at that point. But how do you get it farther away? Well, we have this band called 30 meters, which I'm really fond of. One, it's very lightly used. Two, it's digital only. Three, there's no contesting. Maybe there's no contesting. Maybe you guys are all contesting on it and don't know it. Four, it's got a 200-watt limit. Five, if you look at the propagation maps, it's pretty good all the time. So now rather than trying to pick the right band to get from A to B, and people ask me, what antenna should I get for HF? And I go, depends on what you want to do. If you just want to talk to anybody, get a multi-band antenna, and then at some time of day, there'll be somebody on the other end. But if you want to talk to one person, then get a monoband antenna, aim it at them, and then go read the prop tables to find out when the best time to talk to them is. But 30 meters is kind of the best of both worlds. Now, back to my contesting joke. A friend of mine, Hoop, this is on the internet, right? Hoop, K9QJS. He's a contester. And I love to tease him because I go, contesting, isn't that ham thing where you contact people and then hang up on them? There's even a question, the tech pool, that says, what's one of the things you should do during contesting? The wrong answer is, ask them for the same thing over and over again. What's the other one? Contact them twice to make sure you got it. Now, here's the question for all you guys playing with these new modes that have my call, your call, and a grid square, and you QSO, and then you log it. I think you're contesting. Maybe. And, you know, we're not going to bust anybody on that. But it's that fringe thing that you were talking about. Don't make the software so automated that it just piles up contacts. What I'd like to do is, I think that's a super powerful thing to have packet kind of things that will be local and HF things that work under difficult conditions. But I want to expand it a touch and say perhaps we could get some compressed short messages in there as well. What's the SMS limit for characters? No, for SMS for the phone. It's 160. The original one. What's Twitter? 140. Why? They added a URL. So they chopped off 20. Where does the 160 come from? That's the myth. What really happened was, as cell phones went analog to digital, they needed a back channel for call setup. And it was small, but it was finite. And the marketing people at the phone company said, I love this term, how do we monetize that? how do we monetize that? What's that mean? Well, you know, how do we charge people to use the channel that's just there anyway? And the first thing they had to do is figure out, well, how big is that channel? And it's not based on how many bytes you have left. There was a guy, I think it was in Germany, it was either Siemens or Philips, one of the big companies, who did a study and basically wrote some software to scan the literature. And he came back with, you know, you could pretty much say everything that needs to be said in 160 characters. And if you want to challenge yourself sometime, do the Joe Taylor test. Get a real live message and just work at how succinctly you can prepare that. I'll tell you how not to do it. If you're the Washington State Ferries, and a ferry's late, you'll get the following message. Due to circumstances beyond our control and weather events that we didn't foresee, and the government's limited spending and liability, the San Juan, oh, that's 160. They start with the excuse and never get to the message. That's not how you do it. So 30 meters is pretty good everywhere. I want to build this. Corky just got a little QRP HF rig. I want to do a PoE UDRC and a QRP rig and a dedicated 30-meter antenna. I could use an SDR dongle for the APRS receive side. This is not an iGate, so I'm not violating the one-way rule. And the one-way rule is a good rule to have. And I think that would be an interesting thing to have. So I could be out in a handheld, hit a digi, hit my house with authenticated messaging because I don't want all the traffic gated over. I want to get this specific message out. And out it goes. Now, at that point, that's the front part of the presentation. That's the APRS of things. Questions, comments, thoughts. I'm either a really good speaker or you're really bored. So now, Northwest Digital Radio, what have we been up to? Thank you, Anna, Northwest Digital Radio programmer. Okay, a recent project that popped up. This is not APRS related, but we also sell products in the digital voice space, which is what Hoos talked about. We sell a thing called a thumb DV. It's a USB stick, you plug it in your computer, and it allows you to decode the streams. D-Star DMR System Fusion. We don't provide the software, just the hardware. Let's pause for a moment on that. D-Star DMR System Fusion. All of them use some flavor of Ambi. They are 95% the same. They are 100% incompatible. If the internet worked that way, it'd be like, I'm sorry, you can't go to this website with this browser. Like, oh. And the phone company, oh, you can't dial that number because they're on GTE and you're on ATE. But in the Alexa, Google Home, Cortina space, they've created that model again. They're all internet devices, they all use the same protocols, they all use the same voice, and they are incompatible at some level. You can ask any of them the weather, but you can't play YouTube over Alexa, and you can't buy Amazon over Google. It's a turf war. The XC3006 came because of this incompatibility. HAMS, as a community, said, that's fine, the manufacturers have broken it into camps. They're all going to try to sell you, use our thing and our thing only and not their thing. But HAMS said, well, what if we just built a reflector that could transcode? It could come in on DMR and out on D-Star. And then each channel that logged in could still join in the community of amateur radio. So you could do that if you had 2 thumb DVs. But there is a 3-channel version of the chip available, which unfortunately costs 4 times as much, so the economics aren't there. But nevertheless, some enterprising people in Europe, which I'll refer to as the XLX team, because I'm never quite sure which country they're in, because Europe confuses me because they have lots of little countries, and I can never figure that out. But Hoos would know which country they're in. What's that? Yeah, that one, yeah. That's one of the little countries I'm talking about. So they built this, and they built the software for it, and they put it live on the air, and then they said, well, all the files exist, and anybody who wants to can build one. Except for the fact that to buy the chip, there's a 16-piece minimum at $80 a piece. So you're in $1,000 worth of chips, then you have to have a board run. And we thought about this long and hard because I didn't want to get into this because it's a very small market, but it serves a need in the amateur radio community. So we did our first Kickstarter and we said, okay, if there are 50 souls that want this, we'll do a run. And we got 30. So we rolled it up again and said on our website, off Kickstarter, if we get 30 souls, we'll charge a higher price and we'll do a run. And we got 39. So the run is in place. It's going to pop out next month. And then those 39 units, I built a few spares, they'll go out to people who can now build this community of transcoding reflectors. Now, once again, you could do it with individual units. This just gives you 6 channels on one USB port. So that project's in place. The UDRC, which you've heard mentioned a number of times in the presentations, the little hat radio controller card. Originally, we designed it with an HD15 connector because John Hayes said, you know that Yaesu analog fusion repeater? I bet I can make it do D-Star. And I said, I would do that just for the poking fun at people value. So we did that, we built it, and it's a 15-pin connector because it bolts right up to the back of the DR1X. How many people have a DR1X? Oh, a few of you. How many do you have, John? John's got, oh, other John. John's got 3. So a bunch of people have done, and that's been successful. But that run is on the back end, and it'll be done soon because either everybody already has a DR1X or Yaesu has decided to neuter the port so we can't do it anymore. Unfortunate. So we're going to roll it, and we're going to change to 2 mini DIN 6 connectors. We're going to package it with a Pi in an aluminum case with the SD card, preloaded, configured, ready to go. Web interface, you log into it. And this is a departure for us because the previous version was an experimenter's board. Go get a Pi, go buy an SD card, download an image, go to our website, follow instructions that might go on for a ways of things you have to type to get it configured and working. And people had some success with that. But I got a lot of requests for, can't you do all of this for me? And the answer is, yes, we can. And now we're going to, because we're looking at, well, we're looking at people like Scott in the MCOM market who want an appliance that you can sit down and it just works. Are you going to do both? Can I buy UDRC too? You can buy the board by itself if you want to. Thank you. Packaged up, preloaded. GPS. Now, John has been asking for a GPS since we started working. He wants a GPS on the board all the time. And I fought this because I said, well, you put it in an aluminum case, it doesn't work. Or if it's in your car, it doesn't work. And it's so cheap to buy a GPS that plugs into the USB port in the Pi. And there's your solution, and Basil's using it. And for tracking functions, it's great. But John Hayes said to me, he said, you know, there's these things like JT8, which could potentially take advantage of much tighter time control. And you can't get a USB GPS that'll do pulse per second, which is what you use to calibrate the rest of your system. So we went back and forth. I wanted to make it an option because it was expensive. Not everybody needs it. But if we take the module apart and pull everything apart and just buy the chip, it turns out that the economics are good enough to where that plus say, hold it up, John. So now it's on the board, it's got an SMA, and out of China, we can get a magnetic GPS antenna with a cable and a built-in low noise amplifier. So those just came in, and they're reasonably priced. Now we can make a package that looks like it's gonna work. All we need is that to bias T. So John's gonna go fire those up tomorrow as soon as he gets home, because he'll be all excited because he finally got his GPS. Joe Taylor, is that valuable? Okay. Because you're one of the reasons that he wanted me to do it.
You're the one that allowed me to push me over the edge.
Okay. Operates locally or headless. What do I mean by that? Well, it's still a Pi, even though it's in a box and bolted down. You can add a keyboard, mouse, display. You got a workstation. And Bud, how many guys in Whatcom County are doing that?
Oh, somewhere maybe 40, 50.
Okay. So Bud's got a community just north of here, and you're running FS?
We're FSQ.
FSQ.
And
Okay, an MT63. And they've got a community of hams, and to deal with the configuration issues, they have firmware burning parties where they get together and all burn the SD card, and Bud, who stumbled through the first configuration, now has it down to where he just gets everybody going, et cetera, et cetera, et cetera. So that becomes the digital radio amateur workstation. And recently I was down in San Diego. My daughter and her husband moved to Ramona, and they got a half an acre. We had some time, so like, let's go get your ham station back up. So the first thing we did was go hang a wire antenna off the palm trees by the pool. And then my daughter made us move it. But it wasn't bad. We just put the baling on the other side of the palm tree and adjust the off-center fed to where it wasn't quite as annoying. So she tolerated it. And then he hung his dual band VHF, UHF antenna, he put that in the roof. And once again, if we pushed it back a little bit, you couldn't see it through the arbor over the patio, so it was acceptable. My daughter, by the way, is also a ham. And we got it running, and they have one of these long ranch-style houses, and the best place for the radio was, after looking at feed lines and everything else, was in the shack, the garden shack. It was right there, and it's like, well, that's where it wants to go. Garden shack, we threw an extension cord over the gate, but you know, it's easy to get power to it. It wasn't far from the other equipment. So we got the radios out, fired them up, got our Pi out, loaded it up with FLDG and other stuff, other HF modes, PSK reporter, put a monitor on it, got it all working, and we did that thing that we all want to do, which is like, let's just let it run and see how many stations we collect. And this, we were doing PSK 31 at the time. And then we all know it's like, well, it's 20 during the day and 40 at night. So in the evening, we'd walk out there and flip the knob over. And what we figured out was, really want three things. There are times when I want to operate at the radios, when I'm fully engaged and I want to watch the waterfall and turn the knob and listen to the little beats and bumps. There are times when I want automated operation, at least for receive, like the PSK reporter, where you can just collect stations, or Whisper also, you can just collect stations. But then what I really want is couch control. I want to be able to take my laptop and sit on the couch and drive everything. So I figured out that that's not just what Eric wanted, That's really what I want. How many other people want something like that? So I'm calling that because, like Direwolf, you figure out what you're going to make, and then you spend a lot of time trying to throw an acronym on top of it. Let's see. A digital audio workstation is called a DAWs. So this is a DRAWs, a digital radio amateur workstation. It's composed of an ET&C, a KVM, keyboard, video, and mouse. Rig control, using USB CIV into one of your HF rigs. And then Wi-Fi back to your network so you can drive it all. Now, Direwolf, on the packet side, allows for this because Direwolf has your choice of it's local, it's on a pretend serial port, it's on a KISS port, or it's on an AGW port. And this also gives us something else. Many of the programs, particularly in MCOM, are Windows only, like RMS Express, RDOP. By having the modem on a network port, you can now run it from a Windows tablet and get rid of that dichotomy of, well, all of our stuff's on Windows. No, wait, all of our stuff is on Linux. It now becomes irrelevant because what operating system does your Cantronics KPC 3 Plus run? It doesn't run one. It's all locked up. In fact, it's so locked up, they have 20-year-old bugs they don't fix. So the 1 watt spot, this came out of an issue I had last year. I was sitting there with our club stuff, and they wanted me to put up an Echolink station to our repeater. So Corky did all the software with SVX Link, worked with Basil. They got it running. I put it in my shack. I said, this is great. And then I realized that if somebody came in over Echolink and they were talking and I was transmitting, I couldn't hear the local repeater. And I thought, well, I can get another radio to listen to it. But that's what I need, another radio. And then I thought, what if I bought one of the cheap HTs and took it apart and cobbled it together and made it a thing? And I went, wait, why don't I just build something that does that? So with a watt and who knows what a Moxon antenna is? Ooh, surprising number. What's the chief thing about a Moxon antenna? The front to back ratio is through the roof. So if you've got an antenna here doing all my stuff, and I have a 1 watt transmitter talking to my repeater, and I put it on the edge of the house with a Moxon, I get a little forward gain, which is nice, but I get a tremendous front to back ratio. So now that's out of the rest of my space. So I found on eBay the cheap Chinese modules. Not to say that all Chinese modules are cheap, but I found some, and I ordered them, and we built it, and we tested it, and it works. It's up at Basil's house, it's up to a couple locations, John's tested one. But when we put it in the lab and did the RF testing on it, the unnamed modules performed less than wonderfully. And I had people that said, we don't care, we just want it for 1,200 baud packet. And I said, well, but I do care. I mean, there's, good, bad, and this was ugly. It had some serious flaws on the transmit side, and I'm not talking about spectral issues, I'm talking about deviation issues. And the receiver was totally deaf. But just recently, we got some new modules in, and thanks to Kurt, who's the disaster guy, among other things, who's very involved with search and rescue, he told us about some modules he was using. We pulled those in the lab and tested them. They work much better. So we're going to push that one into production as well. So what about the elephant in the room? Who knows about the UDRX? Oh, only a third of you, so. In that case, we'll talk about it later. That's the one that I burned on 2 years ago. In every project which goes on too long, at some point it becomes a zombie. and it sucks the life out of the people who work on it, or in this case, the people who aren't working on it. But either way, it's always hanging over your head with, well, when are you going to get that done? And after it goes a certain amount of time and doesn't happen, you have to admit that the project's not happening. So it's going to get a reset, but as of now, I'm going to pull it off the website. I'm going to stop talking about it. I'm not going to light myself on fire again, but it may come back in the future in a different form. There's still a need for it. That hasn't changed. It's just a matter of getting the project staffed. Now, in 2012, when I launched it, Kickstarter did not exist. And I have to say that in my almost 40 years now of doing this, if Kickstarter existed 40 years ago, I would have saved a ton of money. Because two things would have happened. Projects I wanted to do would have gotten funded earlier and happened stronger, and projects that weren't going anywhere wouldn't have gotten funded, and they would have gotten killed before I wasted a lot of money on them. Kickstarter's a great thing. Kickstarter, the concept's a great thing. There's other sites that are more tuned. Kickstarter was started with like funding books and photo tours and stuff, movies. But it kind of extrapolated into this hardware space. There's now other sites which are more appropriated for selling hardware. And that brings me back to this. So the key part is putting the amateur back in amateur radio. Because due to manufacturing things, we can still build antennas, we can still experiment there, but due to the nature of service mount electronics, a lot of this stuff, the idea that you can actually, build a kit something, that's pretty much out of the reach for the modern technology. But it's about the community. It's about amateurs who are willing to experiment. What do we have? We have inexpensive Linux single board computers. Yeah, it's a Raspberry Pi, but it could be anything. It doesn't matter. We have standard hardware interfaces. Operating systems have standard ways to talk to devices. You can bring a new device online, you get a driver for it, you can talk to that one as well. And we have open source software. And many people in this room have used it, and many of you have contributed to it. So that's the really powerful thing we have. Just to name a few. Direwolf, things that start with JT. Thank you for explaining FT. It's like, is that Joe Taylor's thing, or is that Frank Taylor's thing, or Frank's thing, or Fred's thing, or something? FLDigi, we haven't talked about it. FLDigi is a great program. It got PSK originally had its own program, Windows only, but FLDigi wrapped it all up and said, let's make it multi-platform, and let's make it a thing where we can plug modems in there so we can keep adding modems easily. SVX Link, that's what Corky did Echolink on. That comes out of the Netherlands as well. All-Star Link is asterisk PBX based. WinDV, BlueDV, XLX Link we talked about. PackLink Unix. PackLink Unix is the shim between a mail client and the WinLink system. What did you write? Oh yeah, it's right here. It's NBuster. So PackLink Unix, this is interesting. So the WinLink system was, the Win means Windows. So it started out as Windows, Windows, or Windows. And they wrote their own mail client, which in my personal opinion is a mistake because we already have mail clients. And then Victor Poor, I believe, was the first guy who did the shim on Windows, WinLink, to get over to a standard mail client. At the time, he was doing Outlook, but that was the shim between the two. And then some folks in Europe did one called, what was it originally called? I forget too. We're all old. It was a shim on Linux, which was not based on their source code because it wasn't open source, but they did write it. And then Basil tried to use it, and it kind of worked. So he picked it up and started fixing bugs in it. And then the holder of the software said, well, you're the guy that's working on it, so why don't you just own it now? So who's used or heard of Pygate? Okay, so Pi-Gate's a little thing that takes a standard mail client, talks to WinLink, that uses Packlink Unix. So when there's a problem, Basil's your guy. Where do we go now? What do we do? I heard FX25 mentioned. So I've read that spec thoroughly. I think that was Tapper 2006 it came out. If you read the top line, it says, this is not the right way to do it. But it is something, and it is fully compatible with existing systems. I contacted them last year and tried to say, do you have a source code repository? Have you done anything? I got nothing back. I went to Tapper, I got nothing back. I went to the satellite communications company, that's their day job, got nothing there. So they just kind of dropped it. If it existed, it would be an easy first step because we could just toss it in there and do the following experiment. John Langner explained to you how bit bopping works, but let's back up a little bit. I got a 128 byte packet total overhead and everything. That's about 1,000 bits. And I get one wrong, and I throw the whole thing away. So that's 0.1% bit error rate. No, wait, it's a 99.9% channel that's useless. That seems tragic to me. So John flipped some bits, but we can do better. In fact, as John mentioned, he put QPSK in there, partly because he was asked for it. But I had a conversation with Phil Karn of some ham note about FEC, and he goes, well, FEC improves anything, but it is more complementary to QPSK in certain mobile applications. Now, Phil's day job until he retired was at Qualcomm. We know what they make. So there's an upside there. So QPSK bumped the bit rate up. Even if you got from 1200 to 24, 36, 4800 QPSK, put some FEC in there, maybe even as low as 3.2, 50% overhead. 50% overhead in FEC, correct me if I'm wrong, gives you roughly 25% bit error correction rate. You get about half a bit back. That would be great. IPv6 has two interesting properties to me. One is header compression, the ability to make a connection and then use a very small header. And it also has the remote protocol, which is designed for very small packets, which are what you find in digital voice. One of the problems with digital voice over IP is the packets are very small, but by the time you get the minimum size packet and the interframe delay and all the overhead involved, you've blown it back up again and you've lost all of that compression over the network. Asynchronous transfer mode. Yeah, little packets. But the argument I always get, and Phil said he was at AMSAT and they wanted him to build another analog modem. And he said, really, another analog modem? Why can't we have a digital modem? And the answer was, well, it's not compatible. But Joe solved that. He solved it because he gave you a free piece of software that is both the application and the modem that runs on a common platform. So now all you have to do to use Joe's software is get the common platform. The same thing exists on the packet side of the world. We now have a common platform. We can now write new modems. No, they don't have to be compatible because any group of us, like your 40 guys in Whatcom, only have to be compatible with the other 39 guys. Exactly. There's none of these guys going, well, it doesn't work with my 30-year-old radio. It's like, well, actually it does. So you have a minimal investment in hardware. The software is free and open source, and we build a community. Joe's last few slides were extremely impressive to me. Look at the size of his community. Look at how FT8 went from nothing for 6 months and just blew by everything else. Now, long term, hams will get bored with that and go, what's next? But that's okay. That's why I want to see some of these things trickle down from the super short QSO mode, which is a good starting spot. So notice the migration. First, it's a propagation tool. It's one way. Why? That's a lot easier to build a system. Next, it becomes QSO based. That's still not connection protocol, but it's a transfer. We don't have to do much to take some of these concepts and be able to pack a few more bits in there. Thank you very much. Question in the back.
APRS of things was about rural and non-Wi-Fi areas more than anything else?
That's one part of it.
One part of it.
The other part of it is areas that have internet, but you don't want to buy one at that location because it might be like I have a well that's 1,000 feet away. I'm not going to buy another internet get up for it.
So there's no technical justification, and second, it's cost.
For that particular application, yes. The other applications are the emergency space where you assume the internet's down. And having lived someplace that survived a 2-week internet outage, as we had one a few years ago, it's pretty amazing what happens. We had a CenturyLink fiber cut on a submarine cable. Now, 911's gone. Phones between islands are gone. Gas stations can't pump gas. ATMs don't work. Grocery store can't take credit cards. The people with the medical alerts, that stuff's all routed off island. Right. Everything went down. B&Bs could not get reservations. If you ever experience it, you'll realize what a house of cards it is. Another example of that, this is a number of years ago, but some disgruntled AT&T employees in Santa Clara County went down a manhole and chopped 3 cables. And everything went out. And all the people went out said the same thing. Well, we don't depend on the internet. We have everything done here locally. And everyone forgot that it was logging into a remote server to get started. Hospitals went down. They all went down. So that's another application space is the we lost the internet space.
Yeah, I got it. But my question is, how do you see the APRS of things fitting in with satellites and mesh network on commercial aircraft and other things that Garmin InReach and other commercial offerings are beginning to address?
Well, first off, okay, so let's take the aircraft one. So I have a friend who runs Island Air Ambulance, and they have a system that tracks their aircraft, and it's the Garmin kind of stuff. And it's tens of thousands of dollars to install, and then it's hundreds to thousands of dollars a month to monitor. And I showed him APRS.FI, and he said, how do I get that? And I said, well, A, you get an amateur radio license, and B, you can't use it for what you want to use it for. Other questions? Come on up, Scott.
Thank you very much, Brian.
You're welcome.
All right, we have another break till 4:15. Again, there's please help yourself to the goodies out there. Make them go away, because none of us really need to take them home. So. All right, let's go ahead and get started. Did it last time.
Who? Me?
Phil.
Oh, Phil did it?
If you went out there and be like, show me some respect, get in there and listen.
No, it's like, okay, we decided to cancel the rest of the afternoon.
Kenny's off the hook.
Yeah, that's it. I'm just going to do the raffle.
Yeah.
Scott's going to live this year.
What's the update on that?
These are different places.
Yes. It's like, which one of those lumps?
Still separates them.
All right, so let's go ahead and get started again. We got one more presentation for you today. We had to swap this one out. This was actually one that was planned earlier. And did you start this? Did you start this presentation at all? No. So we had him on the schedule. We swapped him out. So apparently he didn't even start. So 2 months ago, we said okay, never mind. Well, yeah. And then so it turns out as of yesterday we lost the last speaker. So Kenny's now been scrambling to put together a presentation. Anyway. Kenny was a former president of the MicroHAMS Amateur Radio Club, a former Microsoft employee, and now works for Amazon doing stuff. Doing stuff that we all see, I'm sure, and probably way too often and spend too much money on. So he's also been working with the HamWAN team, setting up nodes, and so we have an opportunity to kind of get an update on HamWAN a little bit and see the construction of one of the more recent nodes. So please welcome Kenny Richards, KU7M.
Oh, man. So I apologize. I honestly didn't plan on doing a talk. I was very happy when I got fired 2 months ago. So I am not an official member of the HamWAN leadership. I am just an enthusiastic contributor. And I mistakenly offered to do a talk about 6 or 9 months ago, and I've now done about 6 or 7 of them for different groups. So I'm going to start by talking a little bit about what HamWAN is, and I'm going to talk about building the node to kind of bridge the gap and kind of fill in the gaps. So, yeah, I have been asked repeatedly what is HamWAN, and I realized when I was trying to explain it that it's not one thing; it's actually 3 different things. So kind of the first bit of the talk is to kind of glue that together. So real quickly, who here thinks they know or could help me explain what HamWAN is? Okay, so you guys don't count. All right, so we'll kind of go through this pretty quickly. I'm assuming everybody at home has a Wi-Fi router and Wi-Fi system, right? That's a pretty common thing. We're familiar with that. That is just a small version of sort of what HamWAN is, to at least definition number 1. So in your house, there's a shelf or a high bookcase, which is where I used to have mine, that has an access point, or a home router, actually, is probably what most of us have. That same thing has, in the HamWAN world, there's an access point and there's an antenna on the mountain that receives your signals. We generally use our laptops or our phones to connect to it. Well, inside that phone or inside that laptop is a Wi-Fi radio and a little antenna, or actually probably a couple of different antennas. Those same things exist in HamWAN world as well. There's a Wi-Fi radio and there's an antenna. These are usually very external. They're obviously mounted outside, etc. And then there's a router piece that routes the two networks together or 3 networks together. So that's really what one definition of what HamWAN is that it's a wireless network. It happens to use the 5 gigahertz band instead of 2.4, a little bit less interference and things like that. and it is built up a series of nodes around the Puget Sound area that are all interconnected. It's IP-based network. It uses something called the 44net public IP addresses, so everything on it is exposed to the public internet. If you have questions about 44net, I can try to answer those later. I sort of know a little bit about that, but not much. John knows a lot though, so I'll rely on him. But it's a network that hams have built in the area for internet connectivity, basically, and also just network connectivity within it. So it doesn't have to go to the internet. It's completely stands alone and can be used for different things. So, real quickly, this is what a client looks like, and what you're actually connected to, or the access point on the other end. So, this is Tom Hayward's rover station. This is him set up over in West Seattle, connecting back. I don't know where he was pointing to. And then this is actually a node up on Beacon Hill that I'm going to talk about a little bit. It's a sector antenna that basically is serving West Seattle, so Sector 3, so it's the southwest sector quadrant. HamWAM actually has two different versions in play right now. This one is actually using the single polarity solution. This is actually double polarity. These are two Microtech radios that service both of them. They'll interconnect, so they work. You just get a little bit better performance and actually just better performance with the dual polarity, which is why they started switching to them. About half of the nodes are on the old one, about half the nodes are on the new one. Do people know what sectors are? Is that a term that people are generally familiar with? No hands, okay. That's kind of know what they are. So this is 5 gigahertz. Line of sight is how they work. You get a lot of benefit with dish antennas. Dr. Taylor talked later about how when they were doing moon bounce, they were 2 meters, and some of the reason for that is they get a lot of gain for when your signal gets louder with a very small amount of whoa. That's cool. Yes, whoa. So the clients have high gain antennas that are very, very sharp. You point them, and it takes a lot of effort to actually point them. The problem, though, is that the radios on the other end, the ones on the nodes, you can't have these highly gained antennas because they could basically talk to a very small group of people that's 1 or 2 degrees wide. So the compromise is they use something called sector antennas that see a section of an area. We actually use 120 degrees. They give about half the gain, roughly. So it's kind of a compromise, but then 120 degree view, they can connect to people rather than a 2 degree view, and they still have a fair amount of gain. Does that sort of make sense? I'm not even going to try to explain how sectors work because I couldn't, but that's generally what they are. The cell phone companies use them a lot as well. But that actually kind of leads to what another definition of what HamWAN is, because whoops, I did crazy stuff with the remote. Leave that over there for now. So HamWAN is also a set of standards. Bart and some of the other people that got started with it sat down and said, we want to build this standard way of connecting ham systems together, and we're going to define how to do it. So there's a set of frequencies. There's basically 10 and 5 megahertz channels that are used, and they define a set of 120 degree views. So there's 3 sectors that make up each node. The neat thing about this, not only can you take your station and point it to one HamWAN node and connect to it, and it just connects, you can pack that up, drive up north and point it to a different one, and it works. Or you can jump on a plane and fly to Florida in Fort Lauderdale, where there's another HamWAN group, and unpack it and point it at theirs, and it will just work. So they've also defined a set of standards for how to wire all these things together. Some of the back-end stuff is different, but the actual client connectivity is all the same, which is actually kind of cool. The third thing that HamWAN is it's also a group here in Seattle. They're a nonprofit organization. They They build all of these nodes. They manage all of the nodes, which is actually quite a bit of work as well. They have an IRC channel that they do most of their operational work back and forth with, but it's also a group. It's technically called the Puget Sound Data Network, but everybody refers to them as HAMWAM. The other groups take some sort of derivative of that. I'm trying to remember, there's a MIM, which is in the Memphis group. There's an Atlanta HAMWAN group. Anyway, there's a whole bunch of them. Most people, though, when they say HAMWAN, they're thinking of the group here in Seattle. So that's well, this is actually a slide I meant to go to. So those are three different things that are all legitimately HAMWAN. That's why it's a little complicated to kind of explain what it is, because you kind of have to realize that it's multiple things. Quick facts, there are 9 nodes in the Seattle area today. The one that's not listed up there that's sort of technically connected to it is that there's also one on Vancouver Island in Victoria. So it's actually international, although it's sort of not us, but it's sort of us. There are 2 POPs in the Seattle area for connectivity backbone to the actual internet. Like I said, everything that connects to it gets a publicly accessible IP address. It's an IPv4 address. So the Weston building is one, and then there's another one in Queen Anne. And I think this list is accurate now. So there's one in Memphis, Tampa, New Mexico. South is actually called the Atlanta group, Michigan, and then the Victoria one that I mentioned already. So yeah, Steve. There could be one in San Diego. I didn't go back and double check the list. So this is a standard slide. So they could be. There are more of them popping up all the time. I was just talked to by someone, I don't know where he's at, in BC that wants to a Vancouver group to connect as well to it. So it's a thing. It seems to be taking over. Yes. Yep. So the other thing that people generally ask is how much does it cost? It's about $250, $300 to put the client station together, depending on how much of the accessories that you have, but that's the radio and the dish cost. The other question is, I haven't updated this either, so hopefully it's mostly correct. This is the overview of the Puget Sound area about our coverage area. So the idea is that anything in red that doesn't have a lot of biological interference in the way, which are trees, should be able to connect to the system in one of those areas. So I mentioned that, I'm sorry for people on this side. The one down here in Olympia, that's Capitol Peak. This one out here is Baldy. There's a couple of them in Seattle. Snohomish, Haystack, the one in Vancouver. I'm talking to people that want to put one up here. So the network is growing and whatever. Here's a view of just the North Sound to kind of drill in. This is what it looks like in the King County in the Seattle area. It's a little crazy. What's very amusing, I have spent a tremendous amount of effort to get connected, and this is roughly where I live. Right in this, it is, I can see the nodes, but I can't connect to them. It's really, really quite annoying. This is what South King County looks like. So as I mentioned, I've been at this a while. So this is my Generation 1 station. It was basically hanging off of the bottom of a mast that had a tribander on it. Whoops, I did that again. For whatever reason, that place was a better place to connect than on the tower itself. So I actually have a 40-foot tower. It worked better there than it did on the top of the tower. And as you can see, I don't have a clear line of sight to Capitol Park. Chainsaw. So that's unfortunately not my trees. So one of the things that I was really excited about last summer was when they started talking about putting a node on Beacon Hill, because I'm thinking, oh, this is much better. It's more southerly. I should have a greater shot. I actually went and upgraded the client node that I had. So this is the dual polarity system. And you can see I still have a problem. So the Beacon Hill wasn't quite tall enough for me to connect to at all. So that's unfortunate. I will figure out a way. So The thing that Scott actually wanted me to talk about was actually building the Beacon Hill node. Like I said, I'm not an official member, but I have gone to several work parties. It's fun to go build stuff because I don't know exactly how this all goes together. I have pieces of knowledge, but not the whole thing. So when the word went out, we want to go assemble the station on Beacon Hill, I'm like, yeah, I want to go help. That sounds like fun. What I didn't realize is that I was going to end up taking it over. So I think we went up 6 or 7 times roughly over the summer. It was something like that. I was there every time. There were times that it was only me and one other person that had access to the building doing stuff, so it was a little crazy. But I learned a lot. I had never used the drill hammer, drill jack, whatever, to drill into concrete. That was way fun. Really, really recommend that. I hadn't got to play with putting together Unistrut before. That was a lot of fun. And then, of course, I also, made cables and wired things together. So when I say Beacon Hill, I realize that there's a lot of people who may not know where it is. So I thought I'd first start by pointing it out. So the Seattle ACS group has access to 3 or 4 sites in downtown. One of them's the top of what's called the Housing Authority building. It's a 15-story apartment building. This is where it's located. I stole this from Google a little while ago. This big thing is the I-90. This is where the downtown ferry is. This is Pike's Market up here. So that's generally where it's at. If you are familiar with the Pacific Medical Building, the big orange one, it's just 2 blocks, I think, from that. It's actually where Amazon was when I started working for them. So the top of this 15-story apartment building, there's an elevator shack. And the Seattle ACS group has a bunch of stuff up there. A bunch of other people have stuff up there. There's a bunch of stuff that no one knows what it is up there. One of the activities that we were doing was actually attaching to all the coaxes. We're like, where does this go? So this is what we started with. Was basically this is our mountaintop basically. So the first thing that we had to do was we had to physically transport all the materials up there. So it's a 15-story building. The elevator goes to 15th floor, but we had to go to the roof. So to access the roof, there's a weird little staircase you have to go up to. It kind of pops out on this door right here. And the first big thing is we had a full-size Dell rack that we had to pack up there. So this is the thing. It's about yay tall, and it's about and it was heavy, and it doesn't fit exactly up the stairs. So the stairs go up to a landing and then turn 180 degrees and come back up. It didn't fit. It had to kind of be lifted over the railing and shimmied around. So it took 4 or 5 of us at least a half hour to an hour to get it up one flight of stairs. Crazy thing is, once we got it up there, we realized this thing is so overkill. We use 2U at the top, and I don't know, maybe that's 6 or 7U on the bottom. So this is actually that's all that's in the rack, and this is a double deep rack, right? So it's way overkill. Yeah. So talk to these guys. They have access. So there's 4 batteries in the bottom that we use for UPS. That's the charger that sits a little self on the shelf. It was funny when we got up there the first day. I was looking at the pieces like, this is stupid the way this is going to be attached. So it didn't actually get online the first day. The batteries were up there. I went back and I built a wire harness and everything to kind of make it work. At the top of the rack, this is a PDU unit that Nigel N7. I had to go look at his name again. NVH, custom built. So he's manufactured about a half a dozen of these now. It's addressable from the internet, so we can turn ports on and off, and does power distribution and everything else like that. This is our Microtech switch, smart switch, that actually wires together all of the radios. All of the Microtech radios are actually little routers, and they do all the normal routing protocols and everything like that. So it doesn't take much to wire the whole thing together. Yeah, the stuff that's inside the HamWAN node or shack or whatever is actually very, very small. And this is a really full-size one because it's got 6 point-to-point antennas and then 3 sectors. Scott, did you have a question? So this is the power distribution unit, right? So we feed this with 24 volts, and it distributes power to all of the devices. So I didn't mention this before, but all the microchips are powered over power over Ethernet. So there's an Ethernet cable that basically runs to the antenna where the radio is that actually powers it and then also carries the network traffic back and forth. This is really, it's a small power supply is what it is, and it both charges the batteries as well as powers the unit when there's AC there. Yes, yes. So Scott actually has one of the nodes in. Yes, yes. That's really bad. Yeah, the nice things about the PDU is that they can turn things on and off individually, and it really makes the whole management thing easier. Anyway. Yes. Yep. So actually, I realize I'm going to talk about how all the things are set up, but I better give you a overview of where and what things are. So in a ham-WAN node, there are 3 sector antennas that cover 120 degrees each. So there's 3. We call them S0 through S3. No, that's not right. S0 through S2. I can't count. So this is S0. It points north. This is actually S1, and this is S2. So that's what you get for making slides too quick. So 3 sectors. There is also a point-to-point dish that connects this node to Baldy. This is actually the first thing that came up, and I'll talk about that a little bit more. This is another point-to-point dish that connects to Haystack, and then there is another one right here that connects to Gold. And there's a 4th point-to-point dish that's in place to connect the Seattle ACS building, and I don't remember what it's called. The EOC, thank you. Yeah. So first day, we actually managed to lug everything up there, and there was existing infrastructure in place that we got the first point-to-point link, and it actually got the node on the air and connected. So there was already Unistrut on the side of the building that we put another piece attached it to. That's the point-to-point dish to Baldy, and all the way at the top of it, that's where Sector 1 is that I installed on the top of it. This is Bart A7J. Sorry, I have to double check this call sign. SJ. He's the one that dreamed up ham-WAN and kind of got the whole thing started. He was there the first day, and then I don't think I saw him again for like 2 or 3 weeks. So, but he said I was doing a job, so why did he need to be there? So we got this corner up the first day, and that got everything connected to the internet. I did the basic configuration of the radios, and then the rest of the network started finding it. We could start, the other admins could do the rest of it. The next thing that we started doing, and this actually took weeks, was getting the Unistrut attached and creating the mounts for the other 2 point-to-point dishes. This is where I learned, fun of giant adult-sized Legos is really what it is. Connecting and making the thing, the mounts for the point-to-point dishes. We originally thought we were going to do another one, which is why this is so tall. It ended up not being that way. This is the one that points to Gold Mountain, and it's also an extremely expensive door sensor because if you open the door to get on the roof, the signal goes away, and we know that someone is up there because the link to Gold, poof, it's gone, and then poof, it comes back. So really, really expensive Internet of Things switch. I don't recommend it, but it does work that way. So these took probably 2 or 3 visits to finally get put all the way together. And it was the weirdest thing. We would have like almost everything except like bolts. I went to Lowe's at least 4 times and bought every single, I don't remember what size it was, every single version of this bolt that they had, and we still ended up not having enough of them. It's kind of crazy. So we got, the Haystack when finally went up and we had to do blah, blah, blah. gold went up pretty quickly. This was the next one that we tackled, and you notice that the building disappears here in the middle. That was the toughest one actually to do the installation. So this is the point-to-point dish that will go to Seattle ACS, EOC, and then this is the Sector 0. Luckily, Bart came back, and he's the one that hung over the top of the building to install these. I didn't have to do that. I don't mind the heights and everything, but I still didn't want to have to do that. So he literally is hanging off the side of the building with the hammer and everything else, drilling the holes and installing the unistrut. He was all tied in, it was all safe, but still he was hanging over the building. So we got that done. And the last one was actually this one that's really Sector 2, even though it says Sector 3. The problem is that there were a bunch of rules about what we could do and not do on the roof. One of them was about anything wasn't supposed to be freestanding. So as you notice, everything else has been attached to the building, but there's no building there. So this is what we ended up coming up with and getting approval for. This is an extremely heavy stand. It takes almost 2 people to carry it, and then there's a bunch of cement bricks. There's going to be a lot of other things going to blow away before this thing does, but it was still out all the way in the corner of the building, so we had to get the Ethernet cable and everything run back to where everything else is. So I found a place that sells these plastic blocks that are like really environmentally safe and all that kind of stuff. You chop them up to the size you want, and they make standard mounts. So there's plastic conduit that's actually what's running it. We had to weight it down in a couple places, but it's actually worked really well. This was, again, one of those things like, I don't know how we're going to build that. I'll figure that out. How hard can that be? So I don't know if this is going to work, but I kind of wanted to give some idea of what things look like. Yeah, so this is a view. Well, these are the different views, basically. So you can see it has a pretty good coverage around the South Seattle over to West Seattle view over the I-90 area, et cetera. That's the view up north in Haystack up there. Yeah, so. Yeah, so, I should have pulled so I actually looked at the graphic, and like within a 2-block radius, I have coverage, but not in my house. I mean, it's just like I perfect it. Yes, that or trees are kind of the other thing. The trees just need to go away. That's really quickly how you build a node. Yes, Steve, but I don't know where Steve's microphone is because I'm holding this one, and Scott just realized. So there, I'll go use the other mic. Go ahead.
Approximately how much was that big antenna that gets blocked by the door? How much does that run, and how much gain did it have?
Off the top of my head, I don't remember. The gain is roughly still about the same. It's still about somewhere around 30 dB of gain. The big radome is really just a cover to make sure that the elements, or if it won't really snow, but that's the standard way of thing is they cover the dishes. It looks like the other dishes on the inside. It's just covered up.
Oh, so it's actually a small dish with a big
cover around it. Yep, and it also helps with interference and things like that. So it provides RF shielding as well. Because remember, the dish only wants to point in one little place over there. Right. Cost-wise, the radio is more expensive. So I'm guessing that each point-to-point link is probably about $450, $500.
Okay. I also heard rumors of...
It's less than that? Yeah, it's under 300. Is it under 300, really? With the radome?
Yes. I bought one.
Okay. So I didn't realize. I haven't paid for any of most of this stuff. So the original, I don't know who paid for all of it, but Hamlin mainly takes donations, and then about 3/4 of the time it pays for the site builds. In some cases, the group that's hosting it or sponsoring it will build it or pay for it. So it's kind of a split model that way. What was your other question? I'm sorry, I lost track of what.
No, that's fine. I also heard rumors that HamWAN Seattle was getting interested in trying to do some 902 to 928 systems?
Yes, there have been people trying it. It hasn't worked so well. Yep, it's way too noisy. Baud has gone down that path a bunch of times. He's trying 3.4 gig now in some places as well. It just hasn't worked yet.
Okay.
In practice, how did you actually point the dishes?
So, in most cases, we could physically see, we knew roughly where it was going, and we would just literally, like, that's got to be close. You log into the radio, and it will tell you, oh, I see a signal, and this is what the signal strength is. And you tweak and adjust, and, you know, when it's as good as you can get, you crank it down so it doesn't go anywhere. Worthless LEDs, yes. So it was funny. Baud actually got the Baldy link working with just the LEDs, and even he was shocked that it worked. But yeah, this particular case, it's really easy because it was a summer, so it was super clear, and we could see where we were pointing everything. Yes. Yeah. So the Dean's idea, and actually I did try this as well. You can use Google Maps and say, this is the point where I'm drawing the line, and then you have it like you scroll it down and you look at what it would be shooting through. It was like, okay, I need to shoot through that guy's that window or that tree or whatever, and then you can get pretty close to it. I'll get you in a minute. Or you have the microphone already? I'm sorry. Yeah, go for it.
So 2 questions. Do you route IPv6?
Yes.
Good. And what is the relationship of HAMNet to AmperNet?
So AmperNet is the organization that a long time ago got a Class A, thank you, set of IP4 addresses, right? So 44net is the other kind of name for it. And AmperNet, I believe, is the organization that administers it. So HamWAN, being a ham radio network, went and said, we want IP addresses. And John, they have a Class B now, right? Right. So John needs a microphone. So HamWAN actually uses a lot of IP addresses for internally management and everything. So they were originally getting small little chunks, and then John finally helped convince them that we needed a big chunk of addresses.
Yeah, so I manage a Class B for Western Washington, and when they were first setting up, we set aside, I forget, 4,000 addresses or something like that, and it soon became apparent that they were going to use those up really quick. So I went back up the chain to Brian Cantor, who controls the whole Class A, 16 million addresses, and we agreed that it would be prudent for HamWAN Puget Sound to have its own Class B. So they actually have a Class B that's one up in the Class Bs from the one the rest of us are using, and they can administer those themselves. They still have blocks on the old one. Eventually we'll probably migrate those off, except for a couple of coordinating channels that they want to be outside their Class B. But yeah, people that are putting together networks that are 256 addresses, subnet, a Class C as we call them, and are planning to BGP, they can contact me. If it's less than that, we'll give you one, but it's not going to be BGP because you're going to be going off through a VPN basically somewhere.
Yeah, so since HamWAN has the technology and has the points of presence, they actually advertise their routes, BGP routes. They have their own AS numbers basically. So on the open internet, when you try to go to one of these nodes, you go down their pipes. Most of the other stuff on AmperNet has to route through the stuff at Berkeley. Is it Berkeley? No. CS. Thank you. Yes. Yeah. Yes, he has retired.
Are you using public unlicensed channels, or are you using special channels and higher power and all that?
So all of the client links are in the ham bands in the 5.6 gig, and that's where all the channels are at. 5.9, sorry. Yeah, 5.9. Some of the point-to-point links are not, and that way they can use the point-to-point links. They can use full encryption, and so may not necessarily, but all of the things where you are connecting the ham system are. Yeah.
How do you ID on the ham band?
Yeah, your SSID. So you actually report what you are, and when you actually set up the radio, say I'm KU7M dash, usually like where it's located. So mine would be like Newcastle, or whatever, and that's every packet you send has that with it.
What are the SSIDs of the nodes?
So that's part of where the standard or the protocol goes. Each one has a standard definition. It's tied to what sector you are and whether it's 5 or 10 meg channel. So I don't remember exactly what each one of them is, but it's a standard definition based on which sector antenna you're connecting to.
No more questions?
So who's interested in going and doing this and thinks that they might be in the right area? That's cool. I wish you good luck. Yeah.
For the hardware, the antennas, what do you recommend?
So the HamWAN site, so the question was what antennas, what equipment do you recommend? So the HamWAN site actually has their current recommendations. So everything is the MicroTics, either the single or dual polarity radios. It's the Metal 5N pluses or the 912, I think is what it is. You can use whatever antenna you want. There's a couple of suggestions about Poitang, if you can still find it, is a really, really good one. I actually I use a MicroTik dish now myself, but you can pick like one of a dozen on Amazon that will work.
There's a plug.
Yes, there are other places you don't have to go to Amazon. Although my son's college fund appreciates it.
Recently. We've had a couple installations we attempted to get, and what's happening is they're sending U.S. versions of the MicroTik radios out right now, and those will not work. So you have to go through special trouble to find the non-U.S. version, the international version, because we had a couple of those we had to turn back because they will not install on the band that is needed for amateur.
So MicroTik started locking down the U.S. version, so they can't go outside of the band, which isn't outside of the band for us, but it is for non-hams. The international versions all still support it. So there's a number of places that you just call them and say, look, I'm a ham, here's my license, and they'll sell you the international version. As long as you're aware of it, it's pretty easy to get a hold of them.
I was worried about that, and I couldn't find a non-international version.
Yeah.
So I'm hoping that their part number was really matching correctly, that it was the international version, and they weren't leaving the suffix off.
Yeah, so there's some people have had no problems at all, and other people have had a big deal. You said you've had a couple. It's 6 of one, half does the other. I so far have not had a problem. I've been able to, every time I've gone and looked, I've been able to get the right one. There was another question, or Dean, did you just want to tell us something?
I just wanted to make a comment. I tried this for a couple years, but it's a pretty inexpensive investment. Was $200 when I did it. I had a problem that I had excellent connection for about 5 miles from February to July, and then it would drop off from July to through February. That's not a foliage growth pattern. Nothing grows, stops growing, blocked my path in July. But it was well worth the time to just experiment. He was jealous because I could aim the antenna during the good period right out my window and hit the DEM. And for a $200 investment, it was well worth the effort. And you get a nice connection free of the internet.
13. We're getting around 13. What were you get for speed?
It varied widely from about 2 megabit up to about 10.
Yeah, that's about what be expected.
If you get a clear shot, it should. I got it.
another proposal for an antenna qua router then. I use a Ubiquiti Air Grid, which is 60 euros. It's like $80. And I have a minus 80 dB signal noise on 11 kilometers. Run from 2 to 14 megabit.
Yeah, the Ubiquiti stuff is really, really good. I don't think that they support the channeling by default, or at least not all of them do. That's one of the reasons why we use the MicroTics specifically. Yeah.
It's impressive to see our long link from South Everett to Gold, right? That's it, 35-mile shot.
Yep.
So it's out across Kitsap Peninsula, south of Bremerton, from Everett, 35 miles.
Well, there's also the one to Vancouver Island.
Well, that's true.
But
too.
granted, it's a lot of sea water, but still, it's even a longer shot.
Any questions? Thank you very much. Oh, whoops, one more.
What's the reliability like as a client? Can I get rid of my Xfinity connection?
No. It's really, really, really the wrong idea that you can replace your Comcast or your whoever internet. There's a bunch of limitations that your normal ham limitations apply to. So using encryption, non-business, all that kind of stuff, which is like a whole other talk that we get onto that I don't want to get into. That's one thing. Reliability is usually pretty good, although this is still amateur stuff. And last 2 or 3 years, there's always been one site that has had a bunch of problems. This year it was Gold. Last year it was Haystack. So Haystack it's been better than it was last year. A piece of equipment's failed on Gold, and it's been completely unreliable for the last month or so. And as soon as they can get back up there, they'll fix it. Haystack last year, we had so much snow that it's a solar-powered site, and they couldn't get enough power generated because all the panels were covered. So they actually fixed that this year by adding wind to it as well. But it's had, when it works pretty well. But it's still not, want to replace your internet with it. By the way, I'm surprised no one's asked why we use it or what you want to use it for. That's usually one of the questions people ask. This is fair. I helped build the beacon site because it would be fun to build it. And I was hoping I could connect to it, but it was still a fun thing to go do.
It's very useful for linking repeaters.
Yes. So far, linking repeaters has been the primary use of it. There are some other things that, so I was scheduled to do,
IP phone. We have an IP phone.
Yes. Yep. And you have video chat too, right? From
we
some
haven't
of the
done
hospitals?
it, but theoretically, yeah. So the IP, we've got IP phones, and I think Seattle has a phone now live. Providence Hospital in Everett has one, so we can 4-digit dial these guys, and it does not touch any commercial service.
Yeah. So I'm going to give a talk at Common Academy in a month or so, and that talk I've actually been planning and working on, and it actually touches more about this is what HamWAN is, and then these are some uses, some real use cases that you can use it to help people start thinking about how they can leverage it, because it is right now a bunch of network geeks that want to build a network, but they haven't really tackled the why are you going to use the network. The repeater stuff has been really, really useful. There's must be a half dozen repeaters that are now linked to it. Yep. Well, Haystack
Kenny?
and Gold are the two biggies.
Yeah, just a couple of comments. One is if you're going to buy radios, this is one of those times it's worth a phone call. Call the dealer, say, do you have the international model? I'm a ham. I'd like to buy the international model. Don't just go order it off the web and hope the part number's correct. Second, for those of you that are into VoIP, telephony, there is now a thing called the Ham Shack Hotline, which you can connect to, and it is a ham radio only network of VoIP telephones. So send me a note if you want some information on that.
Yeah, that's funny. We couldn't find the orientation of the So we went to try to see what we could do on San Juan Island to one of the sites. and there were at least 6 or 7 of us, and we couldn't figure out where north and south was. It was really amusing, and we all realized, wait a minute, Victoria's south of us. Why we're pointing the wrong direction? It was a very amusing day, and then we realized that what we should really do is go to the bar and discuss it. That was a better use of our time. So anyway, real quickly, this is the HamWAN site here in Seattle. The mail list, if you want to join it. Really, if you have questions, they are big on IRC, and they have a HamWAN channel on IRC, and there's someone in there virtually 24 hours a day. They're a little crazy about that. If you have questions for me, that's my email address. But thank you, everybody.